Okay, so time to start. Welcome to this LLMs workshop, which in this case does not mean large language models, but actually large language metaphors. And it is dedicated to new computational approaches to metaphor that are being developed in these very last years, thanks to LLMs now in the most common sense. I welcome in particular the speakers of the workshop who accepted our invitation, but I also welcome all the participants that registered to attend the workshop. We received an unexpectedly enthusiastic and huge response from many different countries. Of course, Italy is the top one because we are based in Italy, but there is UK and Netherlands and Germany, Spain, all over Europe and also the East. And I'm sure that if the time zone would have been more favorable also overseas, there would have been a great response. Many people are looking forward to the recordings. So the question comes, why such a great interest in the topic? And I believe there are at least two reasons why metaphors and LLM is an interesting and attracting topic. And the first reason, I think that it's the following, that metaphor is a cognitively challenging task. We know from theoretical insights that metaphor involves a series of different processes from pragmatic inference to mind reading. They are loaded in theory of mind. They also activate sensory motor processes, and all this comes not only from theoretical insights, but also from empirical research in psycholinguistics, neurolinguistics, cognitive neuroscience of language that shows the cost of metaphor for the brain. And all these components that I mentioned, the inference, the mind reading processes, and the embodied processes are aspects that are known to be critical and challenging for LLMs. So metaphor is a test ground for assessing the linguistic and cognitive capacities of these new generation of machines. But there is a second reason, I think, that makes metaphor and LLM a particularly attractive topic. And it's the fact that the advent of LLMs makes possible to address a series of tasks that, although possible, remain somehow limited and critical. And these include, in particular, metaphor identification and metaphor interpretation and evaluation. And while reason number one, the cognitively challenging nature of metaphor is perhaps more interesting for computational linguists and people in artificial intelligence, these reasons of the new things we can do with LLMs in metaphor research is particularly interesting for metaphor scholars, for psycholinguists and neurolinguists who are interested in addressing metaphor and can retrieve new material, can model new phenomena with these new approaches. We come from this second strand of research. So I want to tell you a little bit how the idea of this workshop came up and was generated. We are doing psychoneurolinguistics experiments on metaphor. We have been doing it in my lab for 15 years. And at the moment, we are hosting an ERC grant that I coordinate, which is called PROMENADE, Processing Metaphor, Neurochronometry, Acquisition and Decay, which is devoted to address metaphor understanding from the point of view of the brain mechanisms, their development, and how metaphor understanding is impaired in clinical groups. So the aim is to provide a comprehensive model able to account for these different domains. domains. But there is an additional word package in Promenade, which is called Figurative Archive. And the aim of the Figurative Archive is to create an archive of metaphorical expression. So the idea was to save the time it takes us to set up experiments on metaphor, because every time we have to build materials, to collect ratings, etc. And so we decided to collect all the materials we used and we created over the past 15, 20 years, and to produce an archive, which we published this year in Scientific Data. And we immediately realized that this archive could be used also as a benchmark, for instance, for LLMs. It could be used as the platform for many application and testing of LLMs. And so we started to work in this direction by using LLMs for rating metaphorical expressions, for modeling neural data. You will hear later from Veronica Mangiaterra on this, and also to perform cross-linguistic research. And you will hear from Ginevra Martinelli later today. So this is the origin of the workshop. While doing this, we came in contact with colleagues that were exploring similar topics and approaches, and we decided to get together to share new insights. Of course, research on metaphor in the computational perspective is much older, and it started well before LLMs, and I think that it is worth to mention the predication algorithm by Kinch, which is probably the first relevant computational model in modern times, based on the idea that metaphor could be captured by semantic distance between words. And based on this insight, combined with many other insights that have to deal with grammatical structure and sometimes with concreteness, imageability, other properties of words, several models have been proposed in the past 20 years. I invite you to check this useful review published in Computing ACM Computing Surveys that basically goes through different models for metaphor identification and for metaphor interpretation that were produced over the last 20 years. The review was published in 2020, so it stops there, and it's undoubtful that in the last 5 years there has been a rise in the topic thanks to LLMs. And this can be seen by a simple search in Scopus by looking for papers on metaphor and computational approaches. You see here after 2023 there's a peak, and the same also if you do a search in the in ACL anthology, you see this peak. There has been challenges over time in metaphor studies and computational approaches. This is the most recent ones, but there were previous ones. So there's a new generation of studies that is developing in this field. And I think that the main advantages that LLMs are bringing to the field of computational approaches to metaphor are the following. First, that we can conduct research on bigger size corpora, and especially that these corpora can be more ecological, can be real and not crafted. Many of the previous models reached a good accuracy, both in identification and interpretation, but on crafted types of metaphor. While nowadays we can address broader corpora and a more diverse types of metaphor. We can also automatically retrieve additional information that first in the past were more effortful to retrieve, like source and target classification, and we can run research on many languages at the same time. Yet the procedures for all this are still unstable. So the idea of this workshop is not only to share new methods, but also to gain some sort of standard in how to use LLMs in metaphor research. Some practicalities. After each speaker's talk, we have eight talks today. We will take a couple of questions from the other speakers. We hope to be able to take also a question from the chat. Yet, please, and I'm saying this to the participants, use the chat, type your questions. We will save them and share them with the speakers. In any case, the recordings of this workshop will be available on our YouTube channel that I invite you to follow, and we will keep people posted on the recording when the recording is uploading, and possibly other initiative on our Instagram page. There will probably be, in a year or so, another online event where we will share our results of the PROMENADE project, not only in computational terms, but also on the brain basis of metaphor. The last words are a thank you to my team at the NEPLab, and in particular to Veronica Mangiaterra and Chiara Barattieri di San Pietro, but especially to Ginevra Martinelli, who took care of most of the organization besides preparing her talk. So without further ado, I think that we can start with the first speaker, who is Matteo Fuoli, presenting a joint work. Matteo, you can start sharing your screen. Presenting a joint work with Weihang Huang, Jeannette Littlemore, Sarah Turner, and Helen Wilding.
All right. Good morning, everyone. Can you see our slides? Yeah, fantastic. Yes. Thank you so much, and thank you very much, Valentina, for putting together such a brilliant event, for inviting us. We're delighted to be here with you all. So in this talk, we're going to present a recent study in which we've tested the ability of large language models to carry out a task that is fundamental for a lot of metaphor research, namely the task of identifying and annotating metaphorical expressions in text. Now, metaphor, as we all know, is a pervasive feature of discourse, and it also provides a powerful lens for examining cognition, emotion, and ideology. Now, for this reason, metaphor has been studied extensively across a wide range of discourses, shedding light on important questions such as patients' experiences of cancer or public perceptions of immigration and national identity. However, metaphor analysis is an extremely time-consuming process because there are currently no reliable methods for automating the crucial yet challenging task of identifying metaphorical expressions in naturally occurring texts. The main reason why automating the analysis of or quantifying metaphor is hard is that metaphor is a very context-sensitive phenomenon. As this simple example shows, many expressions carry a metaphorical meaning in some contexts, but not in others. This is why metaphor researchers, in most cases, have no choice but to manually annotate metaphor in text using tools such as NVivo. And then we end up like this poor researcher here, really stressed, spending a lot of time, many hours coding in NVivo. The problem is that this process is not only labor-intensive and extremely tedious, it's also prone to error. And this fact fundamentally limits how much data we can feasibly process, and by extension, the degree to which our findings can be generalized. But what if we could delegate this process, the low-level task of metaphor identification, to large language models, so that we could annotate much larger data sets, produce more reliable and generalizable findings, and redirect time and resources from low-level annotation tasks to higher-level interpretation and theory building? That is the question that we're tackling in this study. We all know how capable LLMs are and are increasingly becoming. In particular, their really incredible ability to understand and process texts we thought would make them ideally suited to the task of metaphor annotation. LLMs are efficient, they are extremely flexible, they can process large amounts of data for us, and crucially, they don't require advanced programming skills, unlike many of the computational approaches that Valentina, you mentioned. But the question is, are they actually accurate? That is what we wanted to find out in this study. So what we did is we compared three different methods, if you like, three different ways of using LLMs in the task of metaphor identification and annotation. The first approach that we tested is so-called retrieval augmented generation, or RAG. This is where we provide the model with our code book as a knowledge resource and instruct the model to annotate our corpus based on the rules, principles, and examples included in the codebook. The second method was prompt engineering, where we designed verbal instructions for the model to perform the task. And the third method was fine-tuning, where we trained the model on a sample of hand-coded texts to optimize its performance. Now, we compared 10 of the most advanced closed and open source LLMs, including several of the OpenAI GPT models and some smaller open source models like Llama and DeepSeek. To evaluate the performance of these models, we compare their output against our manually annotated corpus of film reviews, which we compiled and created for a previous study. And we used a phraseological approach to metaphor identification, so not the metaphor identification procedure, not the MIP, for reasons we discuss in detail in our paper, and which my colleague Jeannette can elaborate on if you're interested. All of the experiments were run programmatically using the LLM APIs, so we could automate the full process. The paper is in its final stages of review, but if you're interested, you can read the preprint on arXiv. Now, let me briefly walk you through the three methods that we use, give you a bit more specifics. So with the first method, RAG, we gave the LLM the detailed codebook that we created to guide our manual annotation, the manual annotation of our film review corpus, and we instructed the LLM to use it to identify metaphorical expressions in text and tag them using a simple XML tag scheme. As standard practice, we set out the general role or persona for the LLM and the general rules for the task in the so-called system prompt, which is also referred to as the developer prompt. We developed this prompt via trial and error on smaller samples of texts, and also via so-called meta prompting, a technique where you essentially ask the LLM to suggest improvements to a prompt. Next, the user prompt was a very simple instruction. Can you please identify and tag the metaphors in the following text? Now, the second method was prompt engineering. This is probably the most popular LLM technique. In a nutshell, it is about designing verbal instructions that effectively condition LLMs to produce the desired output. We tested three different prompt engineering techniques: zero shot, few shot, and chain of thought. Zero shot is the simplest of them all. The model is provided only with a task description and must rely only on its inbuilt knowledge to generate responses. The prompt we used for this strategy is the same we used for the RAG approach, however, without the second to last sentence in the system prompt instructing the model to consult the codebook. A common alternative to zero-shot prompting is so-called few-shot prompting, where shot essentially means example. The model is given a small number of examples from our corpus showing the correct outputs. So this technique leverages so-called in-context learning. So the model essentially learns patterns from the examples without changing its internal parameters. The system prompt remained the same as in the zero-shot setup. However, the user prompt contained either 4 or 8 examples of manually annotated sentences from our corpus. These examples were structured as alternating user assistant messages. So this is just a technical detail where essentially you trick the model into thinking that it gave the right answer. And so as you can see here, this is just an extract. There were, there was a battery of these kind of gold standard examples. And then the final line was a user message with a blank assistant slot where the model was provided the full text to be annotated and was instructed to do that. Okay, the third prompting strategy we used is so-called chain of thought prompting. These, by the way, are not strategies that we came up with ourselves. We just adapted them from previous work. All the references are in the paper if you're interested. Now, the goal with a chain of thought prompting is to kind of make the reasoning for the annotation more explicit so that the model can somehow learn, not just from the examples, but from the underlying rationale for why we annotated the examples in the way we did. So in this, so the system prompt was the same, but in this case, each of the examples was also followed by a short explanation, as you can see in this slide, that essentially demonstrated why the words that are tagged should be tagged as metaphors. Now, we generated all of these explanations automatically using ChatGPT based on the same exact template for all of the examples, which helped us streamline the process and make everything nice and consistent. In some cases, the examples contained multiple metaphors, in which case we just listed them all together with their explanations. The third approach we tested was model fine-tuning. Fine-tuning essentially means further training a language model on a task-specific data set to improve performance. So unlike prompt engineering, fine-tuning actually changes the model itself by updating its internal parameters. This is done through supervised learning on labeled data relevant to the task, which in our case was 80% of our film review corpus. The remaining 20% was used as a test set to evaluate performance. So how well did these LLMs do? Let's look at the results. The plot on this slide shows the median F1 scores for our LLMs across the 3 methods. As you can see here, the winner was fine-tuning with an accuracy, a median F1 score of 0.79, which is considerable and actually beats a lot of the previous studies that focused on individual isolated sentences and individual words within metaphorical words or expressions within those sentences. So this is really considerable, especially given how difficult the task of metaphor identification is and the fact that humans ourselves often disagree on what counts as a metaphor. The O3 reasoning model performed best for prompt engineering here, as you can see, with a median F1 score of 0.75, and also in RAG with a median F1 of 0.74. Clearly, as you can see, closed source models outperformed open source models. These were relatively small models that we ran on local hardware. Now, if we zoom in on prompt engineering, we find that the best setup was for the O3 reasoning model with a chain of thought prompting and 8 examples, which achieved a very solid median F1 score of 0.76. This suggests that examples plus explicit reasoning steps do help large closed source models perform better. Crucially, this performance is not too far behind fine-tuning. However, with the big advantage that with prompt engineering, you don't need a full annotated corpus. All you need is a handful of examples. Even with zero-shot prompting, reasoning models performed quite well. O3 reached a median score of 0.73. This suggests that these models already have strong internal knowledge that helps them perform the task effectively. Open source models, unfortunately, showed lower accuracy, and as you can see, they were less affected by the type of prompting strategy. They're pretty flat. Like there isn't a reliable difference here. Yeah, so these are the quantitative results in the paper. We provide also statistical testing. Most of the differences that I mentioned are very reliable statistically, which we confirmed using mixed effects beta regression analysis. But of course, this only shows part of the picture. What we were primarily interested in is understanding where LLMs got it wrong and why. So we manually coded a sample of texts annotated by the LLMs and identified several types of errors, which my colleague Jeannette Littlemore is going to tell you a bit more about now.
Hi, thanks, Matteo. Yeah, so just looking at what we call it error analysis, but I should have make a caveat here that we talk about false negative and false positive. So false negative being where the humans got the identified metaphor and the LLM didn't, and false positive being where the LLM got the metaphor but the humans didn't. But that kind of assumes that the humans are always right and the LLMs are always wrong. But as we'll see in some of the data, it's not always the case. Another point to make is when Matteo was introducing it and when we were talking about doing the study, the initial idea would be the LLMs do all the donkey work or the tedious manual stuff and the humans do the clever thinking. Actually, we found that this exercise, this activity has helped make a number of kind of theoretical contributions to the field. And I'm going to take you through some of those now. So basically, as you can see on the slide, we identified reasons for discrepancies between the humans and the LLMs. And we categorized these as according to whether they led to a false negative or false positive. And I'm going to take you through some of the reasons that tended to skew towards, first of all, false negatives, some of the reasons that kind of led to discrepancies in both directions, and some of the reasons that tended to leave more to false positives. But in most cases, it's skewing towards it's rather than absolute differences there. And it's interesting because these reasons, they really tap into some of the excellent work on metaphor and some of the controversies that have been running through the metaphor field for many years. And they also provide perhaps ideas and ways in which when you're annotating a corpus, I think for any kind of metaphor annotation procedure, it's never going to be a one-size-fits-all approach. There's going to be different reasons for doing the studies. There's going to be very different kind of corpora that people are working on, different research questions. So you're going to have to tweak your definition of metaphor in some ways. And these findings from this study give indications of what kind of things may need to be tweaked. And also, I've got a few thoughts about when you might want to tweak them. So starting with the false negatives, it tended to be the case that degree of conventionality would be something that would affect whether humans or LLMs coded something as metaphor. With human coders, I should say the human coders, me and Sarah Turner, who needs full acknowledgement here, would code these things as a metaphor, but the LLM wouldn't. So you've got things like the very near future, anyone who hasn't spent their life in seclusion. So you've got here the idea that the future is talked about in terms of space, whereas spending their life is some kind of like resource. I think that a lot of folk views of metaphor would not code these as metaphor. These are kind of metaphors that are for the metaphor nerds like us. And these are not picked up by the LLM. And it suggests that the LLM is bringing in, as well as the prompt, following the prompts, it's bringing in a folk definition of metaphor, which it's probably getting from all its examples of things that have been coded as metaphor or talked about as metaphor in its database. So here we've got, these underlying conceptual, very, very basic primary conceptual metaphors of size and shape and containment tend to be missed by the LLMs. Another one where we got largely false negatives was in personification. So things like this, the fury Mother Nature can unleash. Here we and Sarah saw Mother Nature as being kind of like talked about as if it's kind of it's got human elements. It can be furious. These were largely missed by the LLMs, and I think this is an example of something where researchers designing LLM models to find metaphor might want to tweak this kind of thing. Personification is notoriously difficult in the metaphor field. It shades into literal. There's great work by Letty Dorst on this, showing how it's hard to decide what the difference is between metaphor and personification. For example, you might want to include personification in the study if, say, for example, you're looking at the way people talk about their interactions with AIs, because a big issue there is whether people see the AIs as human. So that might be an important issue there. But for other studies, personification may not be an important thing. So this is something where you can kind of like shift the cutoff point in terms of what you're going to ask the LLM to look for. Explicit comparisons. These also tended to be missed by the LLM. So about as funny as a root canal. And I think this is because in the kind of folk idea of metaphor, you've got this distinction between metaphor and simile, whereas similes are signalled, but as we and metaphors aren't. But as we know in the metaphor field, there's all sorts of ways of subtly signalling metaphor, not signalling metaphor. It can be done verbally, it can be done through gesture, it can be done through intonation. And so there's not a clear cut-off point between metaphor and simile. That's just not a thing. But the LLMs have still got that in their database. And finally, one that's a really interesting false negative, and this taps into some of Alice Dignan's work, grammatical uses that cue metaphoricity. So here are things that were missed by the LLM. I found this approach to be very clever. She was bathed in soft light. And as humans, I think we have a kind of intuitive sensitivity to the fact that here approach is being used as a noun. When it's being used literally, it's more likely to be used as a verb. I'm not saying this is like 100% black and white categorical, but it's kind of like the patterns. It's the probabilistic processing, if you like, the kind of like, if it's used as a noun, it tends to be metaphor. So humans have this knowledge, the LLMs don't. She was bathed in soft light. Similarly, here it's appearing in the passive voice, and therefore it's kind of processed as a metaphor. Whereas in a literal, it's more like to be, I bathed in the lake. Whatever. So here it's these grammatical cues that the LLMs still are missing out on. Discrepancies that occurred in both directions. A big one here was difficulties in perceiving a source-target distinction. So here you've got this film looks like a prime candidate to join the list of high-concept bad movies. This idea of a list, it could be that somebody has some literal list in their head of high-concept bad movies, but it's likely to be the case that it's a kind of like a metaphorical list. So here's one where we coded that as metaphorical, but the LLM didn't. But you could argue that, yes, there maybe is a list on some level. And here I think this brings into this question of like whether there is, in metaphor, you can always identify a distinction between a source and a target, or whether actually more realistically, it's a blend of two possible meanings, and those two possible meanings are both active at the same time, which I think in the metaphor field people are becoming to realise is a more dynamic, nuanced, accurate view of how people think about metaphor. Source target is a bit of an artificial thing. Phrase level meaning was another thing. So Sarah and I, the coders, we coded a member of that undistinguished club. So this film is a member of that undistinguished club of being like terrible films or whatever this was. We saw this as a scene, a whole thing. So this is following Marlene Johansson Falk's work of these metaphorical scenes where you take the whole idea as the metaphor, whereas the LLM just coded club here. We think that if you just code club, you miss the meaning of the metaphor. In order to get the full metaphor, you've got to have a member of that undistinguished club. So here we have the classic distinction between the MIP and a more kind of like extended word-based or phrase-based approach. So these are all, as you'll see, these are all issues that come up in the metaphor research field time and time again, being exactly replicated in this study with the LLMs, which shows that when LLMs and humans are working together, the same issues occur. And finally, false positives. I'm just going to talk about one of them here. Difficulties in perceiving a contemporary relationship between the source and target that was based on comparison. So in the MIP and in other metaphor identification protocols, there has to be two meanings. The word in question has to have two meanings, and both of those have to be contemporary meanings. One is basic, bodily based, one is metaphorical, and you have to have some kind of comparison. A lot of the metaphors in our study were kind of old ones, they were historical ones, so red herring. So something is a red herring, it's kind of like leading you off in the kind of like direction you don't want to go in. maybe there is some sort of historical meaning there, but it's lost on most people. Most English speakers would not know why we talk about that as being a red herring. People develop folk etymologies, but they never know if they're actually correct. LLMs are picking these things up, and again, it's probably because of this idea. This is a general lay interpretation of metaphor, and it's a valid one, but it tends to be. Because metaphor researchers are often interested in actual metaphorical processing, they're looking for contemporary meanings that people are working with together. And again, this has possible implications for research. So in some studies, these kind of metaphors may not be useful, but in other studies, say, for example, studies of historical linguistics looking at the role played by metaphoric thinking in language change, this kind of thing would be absolutely essential to include. So I think of all these types of errors that we've identified, for every single one of them, I think for the analyst, when they're deciding how to design their LLM-based metaphor identification study, thinking about their research questions, thinking about the data that they're dealing with, they're going to have to decide some sort of cut-off point to tell the LLM for each of these types of errors and give it that kind of decision to make, which I think would help improve the accuracy and also contribute, again, to the theoretical basis of the metaphor identification.
Brilliant. Thanks, Jeannette. Just briefly then, main takeaways. I think our study has shown that state-of-the-art closed-source LLMs can identify and annotate metaphor in full text with a high level of accuracy, with a F1 score of 0.79. Most discrepancies, just like Jeannette has just demonstrated, are not random, but reflect well-known gray areas and ontological challenges in metaphor analysis. LLMs therefore offer a viable means of at least semi-automating metaphor identification and annotation. There's obviously a lot of work still to be done, but all of the these qualitative error analysis results, I think they provide lots of pointers to ways of improving the performance. Yeah, so, and there are potential theoretical implications. This co-work with LLMs could really be actually very productive. Although, as I said, the preprint is available. It's in the final stages of review for applied corpus linguistics, so watch this space. There's also GitHub with all the code, all the results, everything you need to replicate our study. And I want to give a final shout out to one of our brilliant PhD candidates, Bingru Lee, who is in the process of developing a very handy code-free platform to replicate our own study and to do annotation with LLMs without even having to touch Python script, which I think will be really helpful. So watch this space. We will obviously publish this on our socials when it's ready. Sorry for going over time. Thank you very much for your attention, and we look forward to your questions.
Thank you, Matteo and Jeannette. That was really interesting. There are a lot of questions in the chat, but first we take a question from our group of speakers. I see that Antonio typed a question, and well, there are many of them. So I'll start with Antonio, who typed the question, and then perhaps one from some other. Antonio, please.
Yeah, so thank you for your talk and very interesting work. I was curious to know something about what kind of knowledge, additional knowledge, did you add in the RAG model compared to, for example, what you have, for example, in the fine-tuning or in the standard prompting strategy. First question. Second question, which kind of fine-tuning techniques did you use?
Thank you very much for the questions. The answer to the first one is that we gave the model a several-page long annotation manual. So all of this is also available on our GitHub, so you can take a look at it. It's a manual that gives our own definition of metaphor, developed by Jeannette and Sarah, and all the rules that they created to annotate their corpus, the film review corpus. So this is a very extensive document with lots of examples, lots of specific rules. In terms of the second question, so the fine-tuning was done by our co-author and colleague Weihang. I am at the moment, off the top of my head, I don't know the specific kind of, if there is a specific, if you're looking for a specific kind of technique that was used, I can follow up with you on that unless Weihang is on this call and can put the right terminology in the chat. But this was easy to do. You can do it via the OpenAI sort of platform. It's really straightforward computationally. All of these models have an inbuilt facility for doing that quite easily.
So thank you. We have time for one more quick question. And since we took it from one more senior scholar, I would leave the word to Yao Xiu, who is a more junior scholar. And Tatiana and Sebastian, please write it down. We will address them later.
Thank you. Thank you for the talk. That was interesting. My question is about the errors that you contributed very recently to. Maybe the LLMs are using some layman definition of metaphors instead of what we define as metaphors. So my question is about whether you have some the definitions that we use for the metaphors in the prompts or the code book, and whether the LLMs know that, and whether that's kind of improve, like if you have the definition and don't have the definition, whether there's difference in their performance.
I know the answer to that.
Yeah, because it's about
This is again a bit technical. So yes, that was one of the variables that we tested actually. I didn't mention it because it didn't affect the performance. So there was one variant of the prompt where we provided the actual definition from our codebook included in the system prompt, and there wasn't a statistically reliable difference between having it and not having it. We did not try. I mean, we did quite a lot of things in that paper. Next steps that includes tweaking the definition, seeing different definitions, incorporating, trying to mitigate or block out these fault definitions if that's not what we want, refining and trying other things, obviously outside the scope of our paper. But I think this is for us all to try out, and there's a lot that still needs to be done, really.
Thank you. I see that the issue of defining metaphor is still a crucial one, and perhaps in the final comments we can get back to this and discuss it collectively. Thank you, Matteo and Jeannette. And I would move to the second talk of the workshop. So I welcome Simone Mazzoli, Alice Suozzi, and Gianluca Lebani. And Simone, I invite you to share your screen.
Yeah, can you see that?
Yes, perfect.
Okay, perfect. Okay, hi everyone. Thank you to be here. I'm Simone, and today I'm presenting our work on metaphor interpretation in baby and large language models. I'll start by telling you about our research questions. We asked whether language model can truly replicate the variability we see in how humans interpret metaphors. And to answer this, we combined accuracy measures with correlation metrics, and we used a normalized annotation on human-generated interpretations. Second, we compare baby language models with large language models. Baby LLMs are models that are designed to face during training the same quantitative and qualitative limitations a human child experiences in language acquisition. So our title features the word revisited because this work builds on a previous study. Let's briefly look at that. So we built a data set of metaphors taken from the transcripts of the Italian Chamber of Deputies, manually identified using the metaphor identification procedure, standard procedure to identify metaphor in text. And then we built a questionnaire where participants were asked to complete sentences explaining metaphors. So we gathered metaphor interpretations. So regarding LM evaluation, we designed a multiple choice task in which LMs were asked to choose the human-generated interpretation over two implausible distractors. So every metaphor was tested with every interpretation that was provided for it. I show you an example with the metaphor, the Italian Republic with this government is becoming the mosquito coil for businesses. First, you see the human-generated option on top, and then the two distractors following. One featuring a more literal sense, and then the other stating the opposite than the correct option. So aside from the distractors, here are the data we start from today. We have 140 total metaphors, 2,540 total interpretations, and a conventionality ratings of metaphor on a scale from 1 to 5, provided by our participants. So, as we mentioned in the previous experiment, each interpretation was tested individually with the distractors. So, language models could show different preferences for interpretations that have the same meaning. And we wouldn't know that by just looking at the accuracy. For this reason, we wanted a way to account for when two interpretations express the same meaning. So, for example, let's look at the metaphor of the labyrinth. We got some interpretations that look more similar, such as the complex and complicated one. And yeah, to consider this factor, we annotated the raw interpretations using specific criteria to group them together. First of all, we grouped together all the grammatical realization of the same lemma, for example, brucia and sta bruciando. Then we tried to identify synonyms among the interpretations, for example, repellere e allontanare. And then we enforce the synonymy criterion by checking for bidirectional entailment. So if A is true, then B must also be true, and vice versa. That should hold for synonyms. Finally, the interpretations that encoded more than one meaning were counted twice, depending on the groups they were included in. For example, the interpretation è odierno e fa parlare was counted one in the attualità group and one in the dibattito meaning group. So I show you an example. Here you see the metaphor esplosione demografica, population explosion, on the very left. And then on the right, you see the raw interpretations provided by humans. In the middle, you see our meaning groups. We called normalized interpretations. To get a measure of the importance of those meaning groups, we use relative cardinality, that is the percentage of raw interpretations belonging to that specific group. So we could rank meanings by importance. You see here the same metaphor we saw before, the demographic explosion. We saw that the propagation sense has a higher importance, a higher relative cardinality score, and then it's followed by incremento, velocità, violenza, and so on. So we wanted a similar metric for large language models, a metric that showed us the importance a certain interpretation had for language models. So we computed average log likelihood on raw interpretations. Average log likelihood is a probability the model assigns to sentences, and it is always used as a comparison to grammaticality and semantic plausibility judgments in research. And we computed this metric for the raw interpretation, so we needed a way to aggregate them to get a unitary value for normalized interpretations. We did that in two main ways. That is by taking the mean of all interpretations belonging to the normalized interpretation, or the maximum, that is the interpretation with the highest probability. Okay, here the same example. You see the mean average log likelihood scores and maximum log likelihood score. And you see that the maximum aggregation method has higher values because it's like choosing the best interpretation among the group. Okay, now I can introduce you to our models, the models we tested. They are 12 and they come in 3 different architectures that are GPT-2, Llama 2, and Mistral. We have baby models, for example, the Bambini family, which was trained using child-directed speech and, for example, subtitles from children cartoons. Among them, we find models trained with curriculum learning, meaning that in their training data, they saw first easier examples and then more complex ones progressively. Then we have baby MC4 models that are baby language models trained on a subset of public common crawl web scrape. And then another main difference is that we have the majority of models trained from scratch on Italian text. And then we have Lamantino 7 billion that was adapted to Italian. Okay, now that we have a value for model preference and you know our models, we want to ask whether model preferences are fully driven by surface characteristics of interpretations. Because if that is the case, it doesn't make sense to analyze meaning, because they would be fully determined by, I don't know, sentence length or word frequency, for example. Those are the characteristics we analyzed. The length refers to the number of characters a sentence has, and the word frequency is the mean frequency of all words in the interpretation. We computed correlation between those values and the preferences of our model for interpretations. You can see that here. And you see that length poorly explains the preferences of our models, but that word frequency does explain preferences to some extent, meaning that models prefer more frequent interpretations with more frequent words. And that is observed also in human beings. The most importantly is that these characteristics do not fully explain the preferences of our model. So we can analyze whether meaning plays a role on it. So let's test our language models first by computing top 1 accuracy. So here you see the metaphor population explosion, and you see that human beings prefer the normalized interpretation of propagation. Whether some models prefer some other sense, for example, Geppetto prefers the violenza meaning, and then Minerva 7 billion and the Bambini model can properly match the normalized interpretation. So we computed the percentage of times in which we observe these kind of match. You can see it here. And from the plot, you can see that larger models generally perform better. And however, we observe some baby models that outperform larger ones. For example, 2 baby models and a baby MC4 do better than a Minerva model 3 times their size. Another thing to notice is that models perform worse on low conventionality metaphor. You can see that by comparing the relative size of the bars. Now I'll show you the top 1 accuracy when we use the maximum aggregation method. And yeah, you see, you remember that means that using this aggregation method means using the best interpretation among the interpretations of the same meaning. We noticed that all models perform better and that they also seem to improve when facing more unconventional metaphors. The difference between bars are not so evident anymore. Okay, now let's move on from top one accuracy. So before we checked whether the interpretation ranked first for humans matched the one ranked first for models. And now we check the total order of the rankings. So we rank interpretations by importance, and then we compute the correlation between rankings for humans and for models. Here are the correlations, and you can see that for the maximum aggregation method, values are much higher, and that for the mean aggregation method, there's a little alignment, little to zero alignment. We see that larger models perform best. We have two main peaks, one for Lamantino 7 billion and one for Minerva 7 billion. Okay, those were our results. So let's wrap up and go back to our research questions. We found that language models weakly align to human preferences in metaphor interpretation. We also see that tasks with a correct option that model had to choose give us a different view on our model, on how models behave. And that once we look at meaning rankings of correct interpretations, we get a fuller view on model behavior. And we see that models still struggle to fully capture metaphor meanings. We also found that larger models usually do better at weighting meanings, but the differences we saw between baby and the larger models are not proportional to their size. This tells us that curating training data and strategy does have an effect on model alignment with humans. So that was our study that we wish to improve in the future. First, by extending the number of models we want to test, and then by modeling further linguistic factors beyond conventionality. And we also wish to expand our metaphor dataset by increasing the syntactic and semantic diversity. And finally, we would like to further investigate LLMs and human semantic preferences, specifically in how metaphor can create biases in interpretation. Okay, I thank you for your attention, and then maybe there's time for questions.
Yeah, thank you, Simone, and I'm happy to take questions from the other speakers. Yeah, Matteo.
Hi, it's actually a question for me. Thanks very much.
Jeannette. Okay.
Yeah, hi. That was really, yeah, Matteo's not suddenly
yes,
changed.
Because it has my name on the
yeah.
yeah.
Yeah, thanks for that. It was really interesting. I was interested in this. I think am I right in thinking that the model was more likely to interpret explosion as in terms of violence, and the humans was in terms of propagation, so the actual context-based meaning. And if so, I'm thinking that it's actually behaving quite like a human in some ways, because if you look on kind of like the most sort of prototypical meaning or element of meaning of explosion, that would be more about violence than about propagation. And also, if you look at metaphorical, the ways in which explosion is often used metaphorically, it's often used in terms of violence, and so it kind of, they're going for like the sort of more core prototypical meaning in the literal sense and in the metaphorical sense. And this chimes with research that's been done on language learners and how they interpret metaphor in a foreign language. They're more likely to go for like the core, if you think of it as the meaning as a radial category, the kind of the most prototypical meaning, and also children acquiring metaphorical meaning. So in a way, it's not that different. It's kind of quite encouraging.
Yeah, that's very interesting because, yeah, probably the violence sense of explosion is bound to the literal sense, while the propagation one is more context-based. So if we talk about a population, maybe you are more likely to choose, the propagation sense. So maybe it's an important observation that models, smaller models specifically, are more driven to the literal sense or the most the most basic sense of the metaphorical vehicle. That's a very cool observation. I would like to explore it in the future. Yeah.
Thank you. And also drawing on the most common metaphorical sense of explosion, because there's all the work on violence explosions. Yeah. So I think it's really interesting there. It's good. Thank you.
Thank you.
I think that I will take now a question from the chat. There's a question from Agnese Lombardi. She's a postdoc in our lab. Two questions from the speaker. Can you discuss how the difference between mean accuracy and maximum accuracy is informative? Moreover, what is your opinion about the performance difference across models, specifically if we consider baby performing better of some large language models?
So the thing is, if we use the mean aggregation method, we take into account all the variability inside that specific meaning group, meaning that you can express the same meaning through different syntactic realizations. And with the mean aggregation, we take into account all that variability. In the maximum aggregation method, we only choose the best interpretation as a representative of that meaning. So it's really expected that models perform better with the maximum aggregation, because they only choose the best interpretation as a preference for that meaning. Yeah, a model that would also perform better on the mean aggregation system would show us that a variability in syntax does not mean a less preference for that specific meaning. I don't know if I explained that properly.
Yeah, perhaps you can follow up with Agnese at a later stage.
Yeah, sure.
Okay. So I thank Simone and the group for their talk, and I would move to the third talk of today, which is by Sebastian Reimann and Tatiana Scheffler. Please, Sebastian, share your screen.
Yeah. Hello, everyone. My name is Sebastian Reimann. I'm going to present work in progress that I did, or that I'm working on with my supervisor, Tatiana Scheffler, and which leans more towards the data side so far, but yeah, will also involve experiments with large language models in the nearer future. Yeah, I'm going to present steps towards a novel dataset of toxic posts from Christian subreddits. And yeah, I mean, since the title says it, we are talking about toxic language. So I want to give a brief content warning that this talk will contain examples of offensive and harmful language, explicit insults, homophobia, and extreme religious views. So yeah, just to be wary of that. Yeah, then I'm going to start with the motivation why this topic of or why this combination of research on toxic or offensive language and metaphor is interesting. Yeah, there has been work done, for example, by Elizabeth Kemp, who says that metaphors are ideal devices for insults. And this is also backed up by evidence from larger corpora, like by Solopova and colleagues, who created a larger Telegram corpus of offensive language from channels related to Donald Trump, and where metaphor was one of the more prominent ways how people express offensive opinions. And another study was done by Lemons and colleagues, who re-annotated Dutch hate speech corpora and found that they were particularly rich in metaphor, particularly rich in specific source domains, and yeah, so showing that metaphor was also a prominent device there. Metaphor is also interesting since I already mentioned we look at Christian subreddits, and metaphor is interesting in that context because previous study, for example, by Stefan Pilaya, who analyzed like drama and discussions on YouTube, has shown that metaphor is in Christian online communities often used as a vehicle to signal group membership, to signal in and out group dynamics, also done again to attack the out group, so this plays in nicely. And finally, metaphor makes explicit hate speech more implicit, softens a bit, or maybe said that it softens a bit the harmful intention, so to say. And this is problematic for automatic hate speech detection. Since I mean, previous research on hate speech detection has shown that explicit hate speech is easier to detect than implicit ones. So this is also proven by a study by Zhang et al., who were, synthetically creating a data set of metaphorical hate speech, implicit metaphorical hate speech, and those were problematic for state-of-the-art large language models. So that makes metaphor identification also interesting to tie into hate speech or offensive language detection. And what we contribute so far, or what we want to contribute, is a data set of Reddit posts that were specifically sampled to include toxic language, and which were then human annotated for metaphor. We choose to go with toxicity, which is a bit broader and basically encompasses everything that is likely to offend or cause distress, all types of languages that do so. And another part is also then we want to conduct automatic metaphor detection experiments, where we evaluate state-of-the-art metaphor detection systems on toxic language specifically, because I mean there are plenty of data sets out there to evaluate language models and large language models or the performance on metaphor detection, like the Amsterdam Metaphor Corpus or Trophy. But those are very low, so to say, in offensive or toxic language. So this makes it interesting to have another data set that's specifically concentrating on that type of language. Previously in the project where Tatiana and I are working, we gathered a large corpus of different of posts from different religious online communities, both English and German. On the English side, we have two subreddits: the Open Christian subreddit, which is claiming to be more progressively leaning towards a more progressive interpretation of Christianity, and the True Christian subreddit, which is leaning towards a more conservative interpretation, so to say. We took the data from these two subreddits for this data set. In the corpus that we gathered, we stored the data in a TI format with rich metadata that preserves, for example, timestamps, preserves the original thread structure, how discussions unfolded, and quite interesting in the context of toxic language, also preserve the up and down votes. More on that later. Previously, we already did a round of annotation of data from this corpus, but that was where we sampled posts mostly containing family metaphors for God, or family terms, like God is a father, God is a mother, those relatively classical religious metaphors, so to say. Those posts were then annotated via the midway procedure, I guess most of you are familiar with that one. And deliberate metaphor identification procedure to single out, examples that were actually used as metaphor. And the original aim was here to evaluate models on cross-genre transfer, so to this genre of religious online communication, and also to look at the performance on deliberate metaphor specifically. But yeah, I mean, this constructed data set, of course, did not contain many instances of toxic metaphors, so which made it necessary to basically look for toxic posts specifically. As heuristics here, we on the one hand made use of the up and down votes here because we sample posts that received more downvotes than upvotes. We argue that these have a higher chance to be considered toxic. And also as a kind of second heuristic, we had the posts scored automatically for toxicity by the Perspective API, who it gives scores from 0 to 1 for various attributes. Among these is also toxicity. And where 0 is of course less toxic, and 1 is very high toxicity, and we choose to select all posts with a toxicity higher than 0.5. We annotated the data via the MIP SFU guidelines for metaphor. The MIP SFU guidelines are a modified version of the MIP guidelines, or the MIP guidelines eventually. They were developed originally by the group of Maite Taboada, the discourse processing lab at Simon Fraser University, to also annotate metaphors used in evaluative language, a positive or negative evaluation, and the latter one, of course, ties in nicely to our interests. They are stricter than MIPVU in what they consider metaphor, which also ties in nicely with our interests because MIPVU, you might be familiar with that, considers a wide range of terms to be metaphoric that are not really anymore perceived to be metaphors by the speaker or listener, so to say, like these temporal prepositions that theoretically explain a time is a space conceptual metaphor. And MIP as a few would basically single out those. They annotate only content words. They also single out light verbs like take and take a hike, where they argue that this take does not really contain any content. On the other hand, MIP as a few has some fixed phrases that would be metaphoric according to their guidelines, but not according to MIPVU, like the political directions like conservative, etc. Basically, most of the annotation was done by a student assistant at the advanced master's level, also with a background in English linguistics, who was relatively proficient in metaphor annotation and was also involved in previous annotation efforts. And I then supervised him, of course. I'll had a final check, also discussed if he had questions. And that's the data set so far. So far we annotated around 4,000 tokens, out of which a bit less than 20% are metaphoric. This is more or less in line with the number of metaphor-related words in other kind of MIP and MIPVU annotated datasets. But given that our guidelines were a bit stricter, hence that the share of metaphor is a bit higher here in our data. Another interesting observation is that it is notably higher in the conservative Christian subreddit. This is because, and I'm going to explain this more in detail in a second, at least in the sample that we gathered, they much more frequently cite biblical metaphors and play with them, so to say. yeah, and yeah, I'm going to explain some of the, let's say, source domain that were more prominent or more observations with respect to them in our data. Because in previous data sets that were data sets of offensive language annotated for metaphor, like dirt and bad hygiene was one very prominent metaphor, especially, source domain, especially for, let's say, I mean, kind of immoral things to be presenting them as dirty. And I mean, like here, those were also very common in our data, very often, like, I mean, relatively conventionalized ones, like, I mean, like naming negative things as shit or talking about immoral things as disgusting or things that they perceive to be immoral, so to say. As I said, another frequent type of metaphor were these biblical metaphors, where they use concepts or metaphors already present in the Bible and apply them to modern day concepts, like in discussions where they say things like, you see the speck in your brother's eye and ignore the beam in your own. Or quite often they actually refer to modern terms as the mark of the beast. So, and those were, as I said, more prominent in the conservative Christian subreddit, with that just as a side note. Interestingly, one aspect that was very common in previous work on a metaphor in offensive language, or one source domain, is animals, which was often used to dehumanize other people, other groups of people. They were quite rare in our data, and even in the few, I mean, those were the two examples that existed in our sample that could be classified animal metaphor. Even then, they kind of serve different purposes, like the relatively, I mean, fixed, or idiomatic metaphor, like the wolf in sheep's clothing, and also this, I mean, a bit of a like random insult also when you look at the wider threat context of I am God and your dog. It was a bit, random. And so those animal metaphors were not as prominent, interestingly. And a final, quite striking thing that also contributed a bit to the higher share of metaphor in the conservative subreddit was applying to say, not in a sense of physically speaking, which would be the basic meaning according to the metaphor identification procedures, but more like in a sense of the Bible says, or this position in the Bible, this passage in the Bible says this or that, which is often used to then basically justify very hateful or toxic opinions, like in the example that I have here on the slide. That's it for the data itself. I'm going to present some preliminary experiments on automatic metaphor detection. Here we were using so far not the larger LLMs, or we were using smaller language models of the pre-LLM era to BERT-based approaches for metaphor detection. So and relying on fine-tuning and supervised learning, but which were also previous research relatively successful with F1 scores of over 70 for this task. We then trained these datasets on the best performing combination in our work on a cross-genre transfer for metaphor detection, which is a combination of the larger out-of-genre Amsterdam metaphor corpus and in-genre data from Reddit. We used here the one that we annotated before, so the father data briefly spoken. And then, we fine-tuned the model on this combination of data and then evaluated on our potentially toxic data set. And those were the results. So we had F1 scores for both models of around 62. Differences were relatively minor, and also the trends, so to say, are quite similar. They also echo pretty much our results in cross-genre transfer. And yeah, they are slightly better in precision compared to recall, which is a greater problem. And in the error analysis, what we basically find, and what also echoed our previous experiments on metaphor detection for data from those forums or subreddits, is that, I mean, if we have conventional, rather toxically used metaphors, like these examples of shit, for example, that at least a few times occurred in the Amsterdam metaphor corpus, although not quite often, the models immediately performed better, whereas more creative insults were problematic, where, for example, in one example, people referring to like people from the Bible as incels, which is an interesting mapping, but yeah, those are like, and generally those more creative insults were really problematic for supervised BERT-based models. Yeah, as a preliminary conclusion, we say that these heuristics were successful to construct a data set, but yeah, the automatic metaphor detection models still, they echo our previous results, that they are highly dependent on what they see in fine tuning. And of course, for future work, we want to look at LLMs experiments with large language models more closely. Interestingly, so far, on the other data set, the father-mother data set, broadly speaking, it also contained other metaphors. They mostly struggled, but we were also very often using like locally run open source language models that were, as we have also already seen in the presentation of Matteo Fuoli, a bit problematic. And yeah, we want to test further prompting setups. And then we want to expand the data collection a bit more. We have mostly captured explicit toxic language, and so adjust the heuristics to better capture implicit instances. For example, looking at examples that had received a high amount of downvotes, but like low scores by the API. And that's it from my side. Thank you for your attention. And yeah, do you have any questions?
Thank you, Sebastian. I see that Veronica Mangiaterra has a question. And then there's a question in the chat. Veronica.
Okay. Yes, thank you for your talk. I wanted to ask if you, given that metaphors can be a problem in the speech detection, if you think that a previous metaphor identification, like automatic metaphor identification, can help a further hate speech detection, and if you think it can also go the other way around, so if hate speech detection can help toxic metaphor identification.
Yeah, I think that's basically what I think, that like integrating metaphor detection into this process of hate speech detection would serve as a mean, probably, or as a step before the actual hate speech detection to help making these implicit instances of hate speech more explicit, and thus eventually benefits the hate speech detection. Yeah, that's basically what I'm hypothesizing, so to say.
I will take a question from the chat by Daniela Ovadia. Daniela Ovadia, she's an expert in science communication and ethics of research, and she's the ethics consultant of our ERC project. And that's her question. Did you compare metaphorical toxic language with non-metaphorical toxic language and how each correlates with polarization? In other words, does a toxic metaphor amplify the polarization effect up and down thumb reactions compared with equivalent toxic non-metaphorical language?
Yeah, so briefly, so I mean, no, we did not make this comparison so far, but this is indeed also one interest of the larger project where I'm working with, because besides Tatiana and I, there are also two scholars of religion in our project that are particularly interested in these questions on polarization. And yeah, that's also one thing that's interesting to them. But yeah, the so to say, the part of toxic language is in the context of this project is still, let's say, in its infancy, and but this is something that is definitely looked at by us and particularly by the scholars of religion, our project. But so far we haven't done this comparison, but it's a very interesting question indeed. Yes.
Okay, thank you, Sebastian and Tatiana, for the work and the talk. There's now a short break, so everyone can have a moment of rest, and we start back again at 11:15 with the next talk. Thank you. So everything seems to work. Time to start again with the next talk by Bolette Pedersen, Ali Basirat, Alberto Parola, and Susie Olsen. Please, Bolette.
Thank you very much, and thank you for inviting us to speak at this conference. We're going to talk about a new project that we started just a few months ago. It's about exploring metaphors in LLMs with a human-centric and culture-aware approach. We haven't come so far yet, but we will start by sort of explaining some of the plans for experiments on the cognitive approaches to metaphors. And then we will also talk about some of the work that we have actually done, because we've been preparing some data resources for Danish metaphors, and we've also made some small experiments on this data set already. The project is funded by the Independent Research Fund Denmark, and we just started 2 months ago, and it seeks to explore how LLMs interpret metaphorical language and to clarify its relationship to human cognition, linguistics, and cultural background. And we also investigate sort of the inner workings of LLMs when they process metaphors, and we want to compare them to the cognitive processing and thereby strive towards more transparency of what is going on in the models. And an aim is to pave the way for models that do not homogenize language and culture, as we currently see, at least for medium and low resource languages, and that are also more human-centric and inclusive in terms of cultural diversity. I'll leave the word to Alberto.
Okay, thank you. So in this part, I will describe shortly the future plans that we have for the cognitive psycholinguistic work package of the project. So we know very well that metaphors are not just a linguistic tool, but they basically shape how we organize our knowledge, how we think about abstract concepts, so how our conceptual system is inherently metaphorical. And for this reason, metaphors can tell a lot about our cognition. It is also well established that from previous research in psycholinguistics that a metaphor evokes very different processing mechanisms compared to comparable, for example, in terms of complexity or length, literal sentences. And this evidence has been mostly provided by EEG and fMRI studies, and even by some eye tracking study, if not so frequent. We also know well that these differences in processing are mediated by the type of metaphors category we use. For example, we know that novel metaphors compared to conventional metaphors evoke much larger differences. The aim of this project is to build a battery, including a diverse set of metaphors, for example, familiar, novel, physical, mental metaphors, so a large set of metaphors to be used both with humans and LLMs. And this set of metaphors will be presented to human participants in a computerized eye tracking reading task. So we could monitor participant eye tracking patterns while they are reading the metaphoric expression. And the same set of expression will be presented to state-of-the-art LLMs. And then we will ask both human participants and LLMs to provide explanation of the metaphors they have read. And the aim is to compare how humans and LLMs process metaphors with a specific focus on attentional mechanisms. So, for example, what we could do with eye tracking is to analyze which part of the text, for example, the single words, participants pay more attention to when they read the metaphors. And in a similar vein, for example, probing techniques, we can investigate how LLMs attentional mechanisms, for example, we can see at which part of the text an LLM focus more or is more important to make the explanation that LLM provides. So in this way, we can compare, we can test whether, for example, the LLM that resemble more human in terms, for example, of attentional mechanisms are also the one that perform better or that provide explanation more similar to the explanation provided by humans. And the overarching aim of this is to shed light on how LLM and human process metaphors and compare these two different processing strategy and see whether they can be different or similar. Okay, that's all.
Thank you, Alberto. So we will now move on to the part of the sort of preliminary work we did on data resources. And I'm going to present the Danish metaphor benchmark, which we have been finalizing just now. We compiled this benchmark to automatically assess LLM's ability to interpret Danish metaphors. And it now contains 900 metaphors. And I should say it's joint work with the Danish Society for Language and Literature, who host the Danish dictionaries. And we have drawn a lot upon the information in these dictionaries. And the idea is similar to what Simone showed for Italian, to see whether the models can select a correct paraphrase of a metaphor in a multiple choice scenario. So we have one correct paraphrase of each of the 900 metaphors and 3 false metaphors. One is false literal, one is false figurative, and a third one is false contradictory paraphrase of the metaphor in context. So to give an example, if we have a metaphor like a ray of sunshine in a context saying, do you remember how happy and cheerful she was as a child? That could be a paraphrase of the ray of sunshine metaphor. Then we have a literal distractor. Do you remember how she loved the sun as a child? So referring to the concrete meaning of sun. Then we have a figurative distractor. Do you remember what a lucky potato she was as a child? So something also abstract, metaphorical, but a little off to the original metaphor. And finally, a contradiction. Do you remember how cold and reserved she was as a child? So something meaning the opposite of the metaphorical meaning. And we tested this on 7 language models. And as you can see, also similar to Simone's results, the proprietary models perform much better. They have an accuracy of 91%, whereas the open models show considerably lower performance on the data set. You can also see the yellow line in the middle of the picture showing the human accuracy. And you may be surprised that humans here seem to interpret the metaphors a little worse than the proprietary LLMs. And there are several reasons for this. First of all, we only tested this on a small percentage of the data. And we also realized, like, for instance, young people didn't necessarily understand all the metaphors in the data set and therefore answered wrongly. And maybe also there were cases where the human annotators disagreed with the paraphrases that we had made of the metaphors. But anyway, very good performance of the proprietary models, even in Danish. We could also see, we prompted in different ways. So we both prompted where the models were told that it was a metaphor, and also where it was not told that it was a metaphor. And we could see that the distractors worked differently. So when we told the model, when the models were not informed about the target word being a metaphor, they were mostly distracted by the literal distractor. Whereas when the models were told that it was a metaphor, the models were mostly distracted by the figurative distractor, which is interesting and which also follows like the human performance in this respect. The data set has a lot of metadata, which we find quite important. So we both annotate the conventionality level. We don't have a five graded scale as we saw in one of the previous talks. We only have 3 conventionality levels annotated. Is it whether it's lexicalized, whether it is implicit in a main sense of the dictionary, or whether it is a completely ad hoc metaphor, not described in any dictionary. Then we also annotate for the source domain. We can do this automatically because it's drawn from the Danish dictionary, at least for the for the conventional ones. We have this information whether the source domain pertains to agriculture, the nautical domain, the gastronomy domain, the family domain, body, and so forth. And that's very nice to be able to see these patterns at a larger scale. And finally, we have annotated part of the vocabulary as to whether it is unique to Danish culture or whether it also works cross-culturally. And that's, of course, because we're interested in examining how well culture-specific metaphors are analyzed and generated in LLMs. If we first look at the first metadata type, namely ad hoc versus not ad hoc, we can see that overall the 7 models perform worse on ad hoc metaphors, which is not so surprising. It's the same for humans. We spend more energy when we are to interpret a new metaphor that we haven't seen before. So that's also a not so surprising pattern, but interesting to see it in the data actually. When we look into the different source domains, we can also see a little bit what works best. So apparently the models easily interpret metaphors coming from the constructing domain, like this is a building, we have building blocks, all the kinds of metaphors we do relating to buildings. Also the food domain. We were surprised to see that the family domain did not work so well. And sometimes there are some also very idiomatic reasons for some of the source domains working harder than others. And also, again, specificity of culture comes in here. So if some of domains are more related to our specific culture in Denmark, then they tend to perform worse in the models. And we are presenting this at LREC in May, this paper on this work. If we look into the uniqueness, which is also, as I said, a metadata information that we give, the first problem is how do we define whether a metaphor is unique or not to a culture? There are many gray zone examples, and we have chosen a quite restrictive approach in the sense that if we see some differences in what you pick from the source domain, then we consider it culture specific. So to give an example, in Danish, we don't say horse trading, we say stud trading, but it means exactly the same. We take another animal from the source domain and put in. And similarly to being busy as a bee, that's not how we say it in Danish. We say you're busy as an ant. So we take another animal from the source domain and use it metaphorically. So we consider these culture specific because they typically go wrong in the models. And we also tested these in context, without context, and here we manually evaluated the results. So we asked the models to explain what the metaphors mean, and then we manually annotated it from a scale from 1 to 4. And what is interesting to see here you see the results of this study. Green is better, so you see that the cross-culture metaphors are much greener in this figure, meaning that they work much better. This is only tested on Llama and ChatGPT, and going through 1,200 explanations by humans or having humans go through 1,200 explanations was quite cumbersome. So it is a limited study here. But still, you see that definitely the models have problems with the culture-specific ones, even if around 0.5% or 50% of the examples go quite well. So what are the typical things that goes wrong? Well, typical strong Danish cultural norms, for instance, we have this norm of humility and collective equality, which is very strongly expressed in our vocabulary. So we have a lot of words denoting people that do not follow this collective sense of equality. And we have this very negative sentiment to those words. So being high-legged or with a high brow in Danish, you should think that would be positive, but that's actually a negative metaphor, meaning that you are knowledgeable in a very arrogant way. So being arrogant is more or less the worst thing you can be in Danish. So we have many metaphors for that. And that typically goes wrong by the models. They interpret them as positive, whereas they are definitely very negative in Danish. Also, metaphors, concrete metaphors mapping from a concrete source to a concrete target. Typically because of visual resemblance or of sound. So for instance, in Danish, we say railways for braces because they have a similar, they look similarly. And bicycles, as you know, the most popular means of transport in big cities in Denmark, we have many words denoting bicycles that don't work well, that make terrible sounds when you ride them. For instance, like an old squeaky garden gate. And these are completely unpredictable by the models. They simply can't guess what they mean, which is maybe not so surprising because the models currently don't have sound and vision to a large extent at least. So this may change over time. Yeah, then I will leave the word to my colleague, Ali.
Yeah. Hello, everyone, and thank you for the invitation. So I will continue this presentation with respect to another angle of this project, which is about how large language models process metaphors internally. And what I want to share with you is very preliminary results that we have collected through some experiments on the data sets that Bolede just explained to you. So the question that we wanted to address here is whether LLMs take a different strategy when processing metaphor text or not. And for that, we take in, examples of metaphoric and non-metaphoric text, Danish text, and when we encode them through an LLM, and then we take the intermediate activations from the layers of the LLMs and compare them. And we wanted to see whether we see any variation in those intermediate activations when the LLM is processing a metaphoric text or a non-metaphoric text. The comparison here is based on the, Fisher discriminant rate and the cosine similarity, which both are sort of geometric measurements of the differences between those activations. And the other is more like information theoretic metric, which is a variational usable information. And it basically tells us about the amount of information that those intermediate activation provide for processing metaphors. So as I said, data comes from the meta data set that just Bolede explained it to you. And so just to complement here, in addition to text being metaphoric and non-metaphoric, so that's, first is the metaphoric part, and then we have the literal paraphrase of the metaphor. And in addition to these two, we have those three distractors. So the literal distractors, metaphorical distractors, and random distractors. So here are the results that we collected from a Danish Roberta model, fairly small model. On the y-axis, what you see is the values of the variational usable information. And I mean, the numbers scale between 0 and 1. But here, as you see, the values are fairly small. And it means that we see relatively small variations, I mean, when the model processes metaphoric and non-metaphoric text. And those variations, I mean, those small variations are visible in the intermediate layer, so not at the beginning and nor at the last layer. We also observed fairly similar pattern for the Fisher discriminant analysis and the cosine similarity, which typically says that there seem not to be a strong difference between, I mean, between the way that LLMs process metaphoric and non-metaphoric text. However, what we should consider here is that, I mean, the experiment here is carried out on a fairly small Danish language model, and that's an encoder-only language model. But so we have then this question that whether the pattern is consistent across different models and different types of metaphors. So do we see stronger variations for those setups? And the other important point to consider here is that in this experiment, we encode the entire document into a single vector. So, and because of the significant overlap between the metaphorical and non-metaphoric text, we would expect that this load variation might be partly due to the to that high overlap between the context. And the other thing that we are considering to further explore is to see whether, I mean, similar pattern might be visible in human or not. So whether human also distinguish between metaphoric and non-metaphoric content, similar as large language models or not. And in our initial readings, we found some support for that there seemed to be some evidence in human as well that they tend to process metaphoric and non-metaphoric texts quite similarly, particularly for the conventional metaphors. But it's still and quite ongoing research that we are doing, and we hope that we can find further evidence on these questions. Yeah, I thank you for the attention. And we are open to questions if there is
any. Okay, thank you, Bolette, Ali, and Alberto. I see a question from Tatiana and then Sebastian.
Yeah, thank you very much for the presentation. That was very interesting. I think you explained it on this last slide, but just in case I didn't catch it right. So when you compared the activations between the metaphoric and non-metaphoric sentences, did you look only at like the place where the metaphor is being processed, so to say? Because that's what also in humans where we would expect the difference, right? Or I guess the way you said it at the end, you looked at the whole sentence.
That's
so would that be an option to just look at the place where the metaphor is being processed, because that's where some kind of transfer would have to take place?
Yes, yeah, that's a very important point. And so we consider it for that. We need to do some sort of either automatic metaphor identification within the text or do some manual annotation. In the current data set, the correct position of the metaphor in the text is not quite annotated, and it's not easy to, align the metaphorical part with the literal paraphrasing. So that's the bottleneck here. But yeah, that's something that we are considering.
Thank you.
Also because sometimes the paraphrase contains an entire new phrase to sort of rephrase the metaphor. So it's not just word comparison to word comparison. It can be quite more complex than that.
I have a little follow-up, because I was wondering, with this kind of approach, wouldn't you always get differences in the activations, right? If you just compare two sentences, So wouldn't you have to have some kind of other baseline where you compare, I don't know, one literal sentence with another literal similar sentence, or I don't know, right? Just switch some words just to see what the baseline change in activation is if you don't switch to this metaphorical level, but you just switch some words around, right?
But that's also a very good suggestion, yeah, to consider it as another baseline. Yeah.
Thank you.
Sebastian?
Yeah, I have a brief question concerning a smaller Danish Roberta model, and I hope I'm not mixing up two lines of the research that you've done so far. But since Bolette mentioned that there were issues with cultural specific Danish metaphors, does the smaller but entirely Danish Roberta model maybe kind of are these maybe easier to process for the Danish Roberta model compared to the larger but mostly English kind of focusing LLMs?
Well, the motivation for using monolingual Danish model was to make the processing isolated to this language, so that the information from other languages are not propagated through the processing here. But with regard to the size, I would say we just did it because we had it, so that was the model that was available. Yeah. Well, I tried, several other Danish models as well. All are encoder-only models, but the final output are quite similar. So I would say, yeah.
Okay.
There's a question in the chat by Francesca Citron on the graph. I think the graph that Bolette showed with the performance of the models in humans. And she asked for a clarification. The graph show higher accuracy in humans than LLMs. So why did you say humans perform worse? I think it depends on the model.
I said that for the proprietary models, humans seem to interpret a little worse than the models.
Yeah.
But of course, compared to the open LLMs, there's quite a big gap.
Yeah. Okay, thank you to the whole Danish theme, and I think that we can move to the next talk, which is by Antonio Lieto, Gianluca Pozzato, and Stefano Zoia. Stefano, hi, you can share your screen.
Yeah. Okay.
Okay.
Can you hear me? Can you see my presentation?
Yes.
Okay, thank you. So I'm presenting a common sense reasoning approach to metaphor elaboration based on conceptual combination. The main assumption of our work is that metaphor generation and elaboration, both in humans and machines, can be at least partially seen as a common sense reasoning problem. And by common sense reasoning, we mean the set of all the non-deductive or non-monotonic inferences that humans do, which have to do with typicality, typical features, and diffusible knowledge. We can deal to this kind of reasoning by representing concepts in prototype theory. But if we want to go beyond representation and generate novel knowledge, we also need to deal with the compositionality, which is the ability to start from the building blocks of the word knowledge that we already have and combine them to generate novel knowledge. And this is a crucial requirement if we want to generate novel knowledge about the world. Unfortunately, prototypes and composition don't always go well together. We might end up on the so-called pet fish problem because prototypes are not compositional. The problem takes its name from its most famous example, where we can imagine the typical fish and its typical properties and a typical pet. But when we think about a pet fish, we can see that this concept should result by the composition between the concept of pet and the concept of fish, but its representation cannot be obtained by merely including all the typical features of pet and fish. So this is a problem that it's hard to deal both with logical-based instruments and neural networks. And we are using the TCL logic developed by Professors Lieto and Pozzato, which was explicitly designed to deal with this kind of problems. TCL is description logics of typicality for conceptual combination. And it's based on three main ingredients, which I'm detailing in the next slides. So the first element of TCL is the extension of description logics for reasoning about prototypical properties and inheritance with exceptions. So we extend the description logics with a typicality operator T, allowing us to add to our knowledge base assertions like typical Cs are also Ds. For example, we can say that typical students are also Facebook users. And this means that we can also meet some students which don't use Facebook. So this typicality operator adds non-monotonicity to description logics. The second ingredient is the Disponte semantic. This allows us to equip our typicality inclusions with real numbers that represent probabilities or degrees of belief. So now we can say that we believe with degree P that typical Cs are also Ds. And this allows us to reason on typical probabilistic scenarios. We can reason about different possible words. For example, when we reason about this knowledge base, we have three typical inclusions. So we can have 2 to the power of 3, 8 possible words, 8 different scenarios. And we can compute the specific probability of each of these scenarios by computing the joint probability of each typical inclusion. So now we can actually reason about different scenarios, different words, and we have a way to compute the probability of each scenario. The third ingredient is the head modifier heuristic coming from cognitive semantics, where we have 2 different roles, head and modifier. The stronger element of the combination takes the head role, while the weaker element takes the modifier role. And when we combine these 2 concepts, the head concept has priority. So its typical properties have priority during the composition. So taking all these ingredients together, we get a set of selection criteria that allows us to select the most relevant scenarios to represent the conceptual combination. And in practice, when we apply TCL, we start from the initial knowledge base. We compute all the possible probabilistic scenarios for the combination, so all the possible representation of this combination. And then we use these selection criteria to select the most appropriate scenario to represent the conceptual combination. TCL was applied in different contexts, from cognitive modeling to computational creativity, affective computing, and recommender systems. And today I'm talking to you about the latest application of TCL to metaphors. And of course, we know that a metaphor is a linguistic tool where we can express a concept called target in terms of another concept called source. But from a computational point of view, we have at least two problems to deal with. The first is how to represent concepts. And in this case, we can rely on prototype theory, and we can use brief representations based on few typical properties of the concept to represent. And the second question is how to represent this connection between source and target. And in this case, we don't have a single answer. There are several theories in psychology and cognitive science dealing with how humans process metaphors. And here we just want to underline that our approach naturally resonates with categorization theory, where that suggests that humans actually use some kind of conceptual combination to understand metaphorical sentences. So the objectives of our work is primarily to test the TCL logic on metaphors under the hypothesis that it can actually capture some key elements of human cognitive functions used for metaphor elaboration, and to improve the existing resources dedicated to metaphors. And in particular, now we are working with MetaNet, which is a metaphor ontology developed at UC Berkeley based on conceptual metaphor theory. This is the overall architecture of MetCL. We presented it at the last edition of DEcay. So here you have the reference to the paper and the code. And we will walk through these three modules in the next slides. I'm using this metaphorical sentence as a running example. Your mind is a computer. The first step for metaphor generation with MetCL is to identify source and target concepts. This can be done manually if we have annotations, or if we don't have it, this can be done automatically by using MetaNet, which tends to have high precision, but it has low recall. And if MetaNet fails, we can resort to an LLM for this identification task. This is a representation of what the MetaNet ontology looks like. We have conceptual metaphors linked to their corresponding target frame and source frame, and each frame is linked with a set of lexical units. So we can start from the metaphorical sentence, and we can look for the lexical units that appear in it. And if we find some relevant lexical units, we can go up to its corresponding conceptual metaphor. So once we have identified the source and target, in this case, mind and computer, we can go on with generate their prototypical representation. And we do so relying on the ConceptNet knowledge graph, which is a knowledge base about common sense knowledge. And we use both its graph and its vector space ConceptNet number batch. And once we have the prototype representation, we can actually apply the TCL logic to obtain the compound concept, in this case, the mind computer, that is our representation of the metaphorical meaning. We had a human-based evaluation of this metaphorical representations. We asked some human judges to assess if these representations conveyed the appropriate metaphorical meaning, and the results suggest that the system is actually capturing some relevant semantic aspects, even if we might need some further validation against a baseline. And going further, we wanted to compare METCL with LLMs and see if we were able to improve the performance of LLMs. So we designed a metaphor classification task. Given a sentence like he's burning with rage, the task is to identify its corresponding MetaNet class. In this case, anger is 5. And we tested several LLMs, both in zero-shot and few-shot settings. And we saw that METCL could consistently generate representations for metaphors that LLMs were not able to classify under existing MetaNet classes. So our next step was to extend the MetaNet classes by adding some new classes generated by METCL. So we have a refined classification task. And we repeated our experiment using the metaphors generated by METCL as possible classes. And the results show that METCL can consistently improve the LLM's classification performance, both in terms of precision and recall. We also checked if RAG techniques can further improve such results. We tried by building a RAG agent with the two best scoring LLMs, which in our case were GPT-4o and DeepSeek-R1. And we saw that the RAG agent tends to achieve higher precision, but it computes less classification and gets lower recall compared with simpler prompting techniques. As a next step in our work, we are currently developing some multimodal extension of the METCL tool. The direction is, on the one hand, image generation, where we can use the conceptual combinations from TCL to improve text-to-image generation models. And on the other hand, we can think about image interpretation and use TCL to improve the understanding of a visual content. This is a current joint effort with Professor Mehul Bhatt from Örebro University and Professor Jakob Sukan from Constructor University, who is currently hosting me in Bremen as a visiting student. And yeah, this is a visual example of a visual representation of the metaphor, your mind is a computer. We also have an ongoing collaboration with Anna Sofia Lippolis from University of Bologna and Silvia Kappa from the CNR, where we are trying to explore the better ways in which logics and knowledge bases can be used to improve these kind of visual representations of metaphorical contents. So to sum up the main outcome of our work, we developed a cognitively inspired tool for metaphor generation. And we show that its result can complement the existing resources about metaphors like MetaNet. And we can improve LLM's performance in metaphor identification tasks. We also had human judges positively evaluating the kind of representation that we generate. And finally, we want to stress that our system aligns with the metaphor theory of categorization, showing that at least some aspects of metaphorical reasoning may actually involve some conceptual combination mechanisms. So thank you, and I'm open for questions.
Okay, thank you, Stefano, for this talk, which was a bit different from the others. So it's good to have different aspects and notation, interpretation, and generation. I'm happy to take questions. Let's see if there are questions from the other speakers or in the chat. Well, okay, Tatiana. We cannot hear you, Tatiana.
I realized it. Sorry. Thank you for the interesting presentation. Maybe I missed this part, so just a clarification question. So your tool actually generates textual metaphors? Is that what it does right now? Like, and do you rate them somehow, if as to whether they're appropriate or new or?
Yeah, not exactly.
Okay.
When we talk about generating metaphors, we are referring to generating a representation of the metaphorical meaning. So we start from a sentence like "your mind is a computer," and through this conceptual combination tool, we generate a prototype that represents its meaning.
Okay, sorry. Yeah. Thank you.
There's another question from Ali.
Yes, Bolette here. Yeah, I was wondering if you know about the ChainNet resource, which is a lexical resource related to WordNet, where you point out which features from the source domain are taken over to the metaphorical domain. It follows the Dostoevsky's qualia structure, basically. So having 4 dimensions described for each of the source lexical items, and then sort of expressing which of them are transferred to the metaphorical meaning. And I'm asking because we are considering to develop such a resource for Danish and some other languages. So I would be interested in whether you know about it and would find it interesting in your research.
Yeah, well, I didn't know about this resource, so I was taking notes about it. Thank you. But of course, it could be interesting comparing with to compare with other resources, and yeah, because on the one hand, we are comparing with the existing resources to see if we can improve these resources, and on the other hand, we can actually use them to build the representation of the concepts when we build the representation for the source and target concepts. We could use a meaningful resource.
There's a question in the chat from Inna Skrinikova. Does your tool also deal with inferencing mechanisms? I mean, common sense reasoning.
Yeah, I would say we can deal with common sense reasoning, in particular on the case of conceptual combination. In this case, we are. This is what we mean by generating novel knowledge. We generate a conceptual. We generate a combination through the inference in TCL. So making inference in TCL is actually meaning generate combination about starting from the starting concepts.
Yeah. Thank you, Stefano and the whole team for this talk. and I think that we can move to the next speaker. There are three talks now from PhD students that have a bit of a shorter duration, so it's 15 minutes in total. Let's start with the first one by Xiaoyu Tong, Xing Zhang, Pia Sommerauer, Marta Lewis, and Ekaterina Shutova. Xiaoyu, you can share your screen. Yeah, we can see it.
Sorry, everyone. I would
Sorry,
like to.
if Stefano can stop sharing his screen.
No, but we can see.
Okay, yes, but it's better for the registration. Okay, the recording.
Oh, wait. Can we?
Okay.
Is it okay now? Okay.
Yes, thank you.
Okay, Xiaoyu, floor is yours.
Hi, everyone. I would like to share one of my recent works that is a dataset of humorous multimodal metaphor use, or HUMUS. Metaphors are cross-domain mappings in our minds that can be manifested in many different ways. There are linguistic metaphors, of course, which are metaphors in language use. There are also visual metaphors, for example, representing an idea as a light bulb. What we are interested in this study is multimodal metaphors. These are metaphors that involve more than one modality. So, for example, both text and image. More specifically, we are interested in humorous multimodal metaphors. These are multimodal metaphors that help to achieve a humorous effect. Metaphor is actually one of the most common humorous mechanisms, and this makes a lot of sense if we consider the commonality between metaphor and humor. The incongruity theory is one of the most influential theory of analyzing and explaining humor, and it says that laughter arises from the presence of incongruity. Incongruity is something that violates our standard mental patterns and normal expectations. Incongruity is also an inherent part of metaphor use, because metaphors bring together two things that don't belong to the same domain. So, of course, there's got to be some incongruity there. And also, many metaphor scholars actually consider incongruity as an important contextual cue when they identify metaphors in text. But despite this common ground shared by metaphor and humor, there haven't been studies that focus on the interplay between metaphor and humor in the natural language processing community. That is, before our study was published. So in our study, we released a large data set with detailed annotations for humorous multimodal metaphors, and we use this data set to test how multimodal large language models understand these metaphors. We sampled 1,000 image caption pairs from the New Yorker caption contest dataset. These image caption pairs don't have metaphor annotations, so we annotated them from scratch. We designed an annotation procedure that can be summarized into these two steps. The first step is to differentiate between humorous image caption pairs that involve metaphor use and those that don't involve metaphor use. Those that do involve metaphor use are then annotated in more detail. I'm going to skip the first step because it's too complicated for this presentation. And then in the second step, when we do the full annotation for a metaphor sample, it includes the following. First is the name of the conceptual metaphors that are relevant to the humor, and also how this conceptual metaphor is actually manifested in the text and image respectively. We also include a short explanation of how the metaphor use contributes to the humor. And lastly, any other figurative devices that are used that are also relevant to the humorous effect. Since we follow the conceptual metaphor theory and define metaphors as cross-domain mappings, we do consider simile, personification, and zoomorphism as subtypes of metaphor use. But if the metaphor used identified is indeed a case of any of those three, then we do still include them in the other figurative devices. So even if other researchers that are interested in figurative language don't agree with our definition of metaphor, they may still find this dataset useful. On the right, you can see an image caption pair that's not annotated, and this is when it's fully annotated. So for example, for conceptual metaphors, we include as many conceptual metaphors that are identified as possible. So in this case, there are two. The moon is a person and mind is a container. And for the image annotation, we do both bounding box annotation and a label that is a word or phrase that correspond to the bounding box. In our dataset, we identified 558 metaphorical items and 382 non-metaphorical items. There are also 60 that are currently marked as discarded for various reasons. For example, because the annotator doesn't understand the humor of the image caption pair, or because it's a duplicate of an already annotated item. We have quite a few interesting findings about the dataset. I would like to share two of them here. This figure shows the conceptual metaphors identified in the dataset. We identified around 390 conceptual metaphors. The most frequent ones are animals are humans and humans are animals. In addition to animals are humans, we also found metaphors that compare other target domains with humans, for example, objects, God, aliens. And these make personification the most frequently used metaphor type in our dataset, accounting for about half of the metaphor samples. Another interesting observation is about the directionality of metaphor. So when we identify a conceptual metaphor, we have to decide for the two conceptual domains which one is the target domain and which one is the source domain. These two domains are not interchangeable. What this means is that, for example, if we say life is like a box of chocolates, life is the target domain and chocolate is the source domain. If we swap these two domains, making life the source domain and chocolate the target domain, then it actually creates a new metaphor. In this case, we say that the metaphor is unidirectional. In previous studies, that is, previous studies done by other people, it's found that this rule of unidirectionality applies to prototypical metaphors of all kinds and occurring in all media, with very few exceptions. What's interesting is that we found a number of such exceptions in our datasets, especially with regard to the humans and animals domains. For example, here, the image shows a bunch of animals having a meeting, and the caption is, "Let's keep this brief. I've got to get back to staring out the window." Here we can have two different interpretations for the humorous effect of this image caption pair, depending on how we interpret the direction of the metaphor. So we can interpret it as using the animals are humans metaphor, or we can also interpret it as using the humans are animals metaphor. And both interpretations are humorous, and this double interpretation adds a deeper level of meaning to this image caption pair. So we hope that this dataset can be useful for people that are interested in the directionality of metaphors. For model evaluation, we tested 6 models, including 2 closed source models and 4 open source models. We designed 6 tasks that correspond to the 6 types of metaphor annotations in our dataset, excluding the annotation about other figurative devices. One of the findings is that the models are not so good at these tasks. For example, in the classification classification task, which asks the models to determine whether the humor of an image caption pair involves metaphor use. All 6 models are prone to classify the image caption pair as metaphorical, so there's a lot of false positives. I'm going to skip through the other 5 tasks and go straight to another experiment where we compare model performance with human performance. We had a second annotator who's also a metaphor, as an expert in metaphor. And we had this annotator provide these 4 types of annotations for about 1/3 of the data set. We then used the same annotation guidelines to prompt the models. Our finding was that the agreement between the models and ground truth is lower than the agreement between the models' compromised performance is indeed a result of their lack of capacity to process humorous multimodal metaphors instead of the subjectivity of the tasks. We also did some ablation study and error analysis, but all of the details can be found in the most recent version of the paper, and the dataset is publicly accessible on GitHub. Thank you.
Thank you, Yaoxun. I think that we have some minutes for question. There's a question from Sebastian.
Yeah, maybe out of curiosity, and I hope I did not miss it, but I saw on the slide that you had quite a good amount of like Whitley annotation. So when in
Yes.
doubt, leave it in the data. Can you maybe or like given or like do you have an explanation why the number is so high? And did that affect somehow classification? So did the models struggle more with Whitley or less? I mean, given that you had many false positives, probably that was not affected, but I'm still curious.
Yeah, it's a good question. It's actually one of the things that's left out. So in the first step, when we decide whether an image caption pair involves metaphor use, we do have yes, no, and Whitley. But here we have this category only because, of course, the annotator cannot be 100% sure sometimes. So we still consider them maybe metaphorical just to have them fully, just to have a go to fully annotate them. So if we can fully annotate, like to have annotation for all of the things for an item, then we consider that a valid metaphorical item. So anything that's fully annotated, even if it's Whitley from the beginning, we still consider that that's a yes.
Yeah, that's reasonable. Yeah, because we operated in a similar fashion that, I mean, Whitley was also more tending then towards yes in many mid-view cases. But yeah, I was just so.
There's a question in the chat from Luca Bischetti. He's an assistant professor in our lab, actually, and he's an expert in humor studies. Do you think that this comparison of domains closely resembles the taxonomies of script opposition, normal versus abnormal, possible versus impossible, proposed in the framework of the general theory of verbal humor, the Attardo taxonomy?
I'm sorry, I don't fully understand the question.
The question is basically how your distinction relate to the distinction that are proposed in the general theory of verbal humor by Attardo, the script opposition.
Oh, in that case, that's a very good question because we haven't considered that. And thank you for the question. I'm going to consider that to improve the paper.
Yeah. I think it's interesting to put the metaphorical theory and humor theory in a close contact with each other, since humor is at the center here.
Yeah.
Okay, thank you, Xiao Yu and the whole team. And I think we can move to the next talk, which is a talk by Veronica Mangiaterra and from our lab. Veronica, can you share your screen?
Yes. Can you see it?
Yes.
Okay.
Great, you can start.
Okay, so now I will present you of our studies that examine the role that LLMs can take when we examine the metaphor processing in the brain, so psycholinguistic approaches to metaphor. And in particular, the two roles that I will present are LLM as participants, so the ability of LLMs to mimic human behavior and to as participants, and LLMs as models. So the possibility of using LLMs as implementation of theoretical accounts. So in the first study, we will look at whether if LLMs can generate valid and reliable ratings for metaphorical stimuli, and whether in the second study, we will see whether LLMs and also other computational models can help us describe the EEG components of metaphor processing, so the electrophysiology of metaphor processing. So starting with the first study, we collected metaphors and ratings for Italian from the Figurative Archive. The Figurative Archive, as also Valentina introduced, is a resource with around 1,000 metaphors in Italian with ratings. And also we collected metaphor and ratings from 3 studies in English. Metaphors are of different forms, so A is B, A of B, and pair of words, and they were rated by human participants along 3 dimensions, such as familiarity, comprehensibility, and imageability. Usually these ratings are collected to predict behavioral or electrophysiological responses. So we also have reaction times and EEG responses from human participants to see whether also GPT-generated ratings can predict these human responses. So first of all, we assess the validity of these ratings by correlating with human-generated ones and see if they show the same pattern, and also what we call a substitution analysis, so to see if they predict human response time and EEG response in statistical models. Then we assess whether these ratings are stable across independent prompting sessions. So let's look at the results. First of all, the correlation between human and machine-generated ratings. You can see that the correlation are quite good, especially for the bigger models, so GPT-4o, while the smaller model, GPT 3.5 Turbo, has a bit of lower performance, especially when we look at familiarity in Italian. So Italian, it struggles a bit rating Italian metaphors. And also you can see that imageability is a bit the most difficult dimension for models to rate, and it has like lower alignment with human participants. Then we also check whether LLMs perform in the same way with different type of metaphors that have different sensory motor contents, so physical versus mental metaphors, body-related versus object-related, motion versus auditory metaphors, because we know that LLMs can struggle with dealing with the sensory motor aspects of word, and so we see whether these impact metaphor rating. And a bit also with the Danish metaphors, we also find that sensory motor aspects are indeed a weakness, and metaphors are rated with higher alignment when they are more mental and less embodied. Then we check whether GPT-generated ratings predict human reaction times and M for under amplitude. You can see the human ratings here in this gray color And you can see that GPT-4o mini and GPT-4o specifically have the same pattern of prediction. So higher familiarity both by humans and models predict shorter reaction time and reduce negativity in the electrophysiological responses. So quite satisfactory results in this domain. Then you can see also that this is the correlation between LLM-generated ratings across independent session, and you can see that it's very high and a bit lower when we prompt the model through the ChatGPT web interface versus the API settings. So to wrap up these first studies, we can see that that ratings obtained from LLMs can achieve high to very high validity, excellent reliability. And they can also be used when we want to predict behavioral and neurophysiological responses to metaphors. Obviously, we have to take into account also the weaknesses that are related to imaginistic dimensions, such as imageability. So we have to be careful if we want models to rate metaphor for such dimensions, and also regarding the content of metaphors. So metaphors that are rich in sensory motor content can be a weakness for models. So moving to the second studies, here we explore the role of LLMs as models. So there are different theoretical accounts that have been proposed to describe how metaphors are processed. Some of them focus on the semantic operation, some other are more pragmatic inferential operations, some other on the predictive mechanism. We want to disentangle the contribution of this operation in metaphor processing via computational modeling. So here you can see a typical component of metaphor processing, the N400 that occurs around 400 milliseconds after word onset and has a negative polarity, P600 that occurs after 600 milliseconds and has a positive polarity. So these three theoretical accounts, the more semantic one, the more pragmatic inferential, and the predictive one, been variously linked to these components. So we operationalize these three models via distributional semantics for the semantic account, LLMs that are trained on next word prediction to implement the predictive account, and we resort to rational speech acts, that is a framework that formalizes pragmatic inference to operationalize the pragmatic account. Then we use measures from these three models to predict the EEG response, in particular the M400 and the P600. So we collected EEG responses from 55 participants that were to read such type of sentences, so metaphorical, in our times, hopes are stars that light the soul up, the literal counterparts, so those lights in the night sky are stars, distant galaxies. For each of these stimuli, both the metaphorical and the literal ones, we collected surprises from LLMs. So how predictable is the target words, for example, stars, given the context, such as in our times, hopes are. Then we collected semantic similarities, so how similar is the target word compared to the average vector of the context. And from the rational speech acts framework, we derive this Bayesian pragmatic measure. This is a measure of the pragmatic load, how much inference the listener have to make to derive the interpretation of the metaphor. And then, so we have the condition, literal versus metaphorical. For each stimulus, we have the three measures implementing the three theoretical accounts. We use them to predict the two main components of EEG response to metaphor, the M400 and the P600. Well, looking at the results, we found a classical biphasic response to metaphors, so an N400 follow a P600 as we expected. But let's go see the effect of the computational measures. In the N400, we found that the best model is the one including both surprisal and the Bayesian pragmatic measure, with higher surprisal linked to greater than 400 and higher pragmatic load again linked to greater than 400. While in the following window, the P600, we found a combination of the three. So a combined effect of surprisal, of the Bayesian pragmatic measure, and of similarity. Notice that, contrary to our expectation, semantic similarity has this behavior such as higher semantic similarity. So when the target word is closer to the context, we have a higher High-Fort, let's say a greater P600. So that was a bit unexpected for us. And try to wrap up this second study. No straightforward functional distinction between the M400 and the P600 emerge, because we see that both predictive and inferential processing plays a big role in both time windows. But what emerged is, for example, a proximity paradox. So that sometimes when a word is too close to the its context, the literal meaning can be competing with the metaphorical one, and it can be more effortful to derive the figurative interpretation of these closer sentences. So again, this points toward a nice integration of computational modeling to describe the electrophysiology of metaphors. So, as general take-home points from these two studies, LLMs can be beneficially integrated in psycholinguistic approaches to metaphors, and in particular, they can act as participants, and so they can accelerate the experimental pipeline and provide ratings for experimental stimuli, and also as models, allowing us to test in competing theoretical accounts of metaphor processing. So these are the themes behind the two studies, and if you want to read the preprint of the first studies and some other recent works from our lab, for example, the Figurative Archive, you can scan this QR code. And I'm happy to take any question now.
Thank you, Veronica. Yeah, time for questions. I cannot answer one. Tatiana.
Thank you. Thank you very much for the presentation. I have a question for the second study and for the models you used for the surprisal. Can you briefly say what kind of LLM you used to compute the surprisal? And also, have you thought actually about downgrading this? Because I heard some presentations recently and read some research that actually smaller or more simpler, older models like even GPT-2 can be better at predicting like actual human surprisal than, you know, the more complex, newer models.
Mm-hmm. Okay, yes, that's a very interesting question. First of all, we use 4 different LLMs, GPT-2, indeed, the multilingual GPT, Minerva, and the Llama 3.2. They are all quite small model, let's say, within the domain of LLMs. And we selected them to be models that could be run on a normal PC. And the best model, the one, let's see, of which I reported the results is the multilingual GPT, but followed by GPT-2. So indeed, the smaller models still have a great predictive power in electrophysiology.
Thank you.
There's another question from Matteo. You're mute.
Sorry about that. That was a fascinating study. Thank you very much, Veronica. Just 2 quick questions. One is, how did you word the question to get the LLMs to rate your examples? And the second question is, can you explain, unless we missed it, how the pragmatic load is calculated? That was, yeah, we were curious about that.
Yes.
Thank you.
Yes, given the short time, I briefly mentioned but I can go back to it. So the Bayesian pragmatic measure is inspired from the rational speech act framework when you start from a prior belief that is usually literal. So we started from the semantics, indeed the semantic similarity between the target word and its context, and then you have a likelihood of updating this prior belief in the original framework. And we use ratings of familiarity. So how familiar is a certain vehicle to communicate a certain characteristic of the topic to update the semantics that we use as prior. And we use the exponential function of both these measures to ensure that we have all positive and uptrending values. As for your first question, we minimally adapted the instruction we given to human participants. So we used the definition of the measures, and then we asked the model to provide a rating from, for example, 1 to 7, and say 1 very low familiarity, 7 very high familiarity, and then we deleted some part of the original instruction that were related to lab settings, so which button to press. So yes.
Great. So did you get like plain, just straight numbers? Was it, did you have to do something to kind of, I don't know, weed out, you know how, yeah, LLMs like to add, oh, that's a great question, blah, 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 you know.
Yes, we act on the verbosity of metaphors in 2 ways. First of all, we ask in the prompt to limit the answer to only the number. And then we also set the maximum number of token to be produced to 1. And so we got just the number responses. And then to mimic the continuous nature of the human ratings, because obviously human ratings are the results of the average across multiple participants, we got the probability of the top 3 most likely ratings. So for example, if the model say, I would say 5 with 90% probability, I would say 4 with 9% probability, and we use the probability as weight to get a continuous rating. So it was more in line with the nature of the human data.
Fascinating. Thank you.
Okay.
Thank you, Veronica. I was checking if there are questions in the chat. I don't think so. And so we can move to, oh yeah, there's a question now. Is by any chance this study published? Well, Veronica, you can say that there are preprints.
Yes, there is the preprint of the GPT ratings, and I can link it in the chat.
Yeah, for the second one, there will be soon a preprint. Okay, thank you. And we can move to the last speaker of today, which is Ginevra Martinelli with a study from our lab. And Ginevra is speaking in addition to organizing. So she had a double load for this event. Ginevra, please.
Thank you. Yes, can you hear me? Yes.
Yes.
Okay, perfect. So yes, today we'll be presenting the project MetaMap, mapping metaphors across languages and cultures. So as you know, as we have said today, metaphors also are a kind of loose use of language in which one thing is regarded as something else. However, according to conceptual accounts of metaphors, they're not just linguistic forms, but they reflect the cognitive mappings that exist between conceptual domains. According to these accounts, some metaphors are considered primary and are claimed to be universal or near universal because they're grounded in some near universal bodily experience we have of reality. So some example could be dominance is height or good is bright. However, at the same time, many mappings are shaped by cultural and linguistic context. For instance, I report here a study by Jeannette Littlemore. She reported the experience of overseas students who struggled to understand lectures when metaphors used by the lecturers were not shared within the students' cultural background. So this suggests a kind of tension between nature and nurture, between cross-linguistically stable metaphorical mappings and language-specific variation. So a similar tension has been explored quantitatively in word meaning association. I report here the study by Jackson and colleagues who compared emotion semantic networks across more than 2,000 languages using collexification, and they found both a universal common structure but also cross-linguistic variation, with valence of the emotion predicting the semantic organization of the emotion across languages family. So from this perspective, metaphor remains kindly of unexplored. There is no systematic large-scale investigation that has quantitatively assessed the degree of cross-linguistic stability versus language-specific variation in metaphorical mappings across different language families. So that's where large language models come into play. In fact, their development and their improved ability to process figurative language now enables to collect large-scale metaphor data through a bottom-up data-driven approach that captures the actual realization of metaphors and not just preselected primary or conceptual metaphors. So the MetaMap project aims to leverage LLMs to build a map of metaphor mappings by processing large corpora to assess how and to what extent metaphors vary across languages of diverse language families. So in particular, we had to go through a few steps. First of all, we had to identify a set of possibly universal target domains, to collect the data of different textual data from different language families, to develop an LLM-based pipeline for metaphor detection, to actually extract and categorize metaphorical mappings, and to perform a cross-linguistic analysis of the mappings extracted. So concerning the first step, so regarding the choice of the target domains, we decided to start from the domain of emotions. In fact, emotions are richly lexicalized across languages, and they're considered a kind of highly metaphorical domain. In fact, people usually use metaphors to express this kind of complex emotional experience that would be difficult to describe literally. So we selected 12 emotion concepts that are frequently discussed within metaphor research, and you can see them here. Instead, concerning the data, we extracted 300,000 sentences across 27 languages from the Leipzig Corpora collection, which is a multilingual repository, which is homogeneous in terms of genre. So we took only news and web text, and the 27 languages were selected to represent major language families in terms of number of speakers, but also for comparative purposes. And obviously, another criterion was data availability. Concerning the models, we considered different options, but we selected GPT-4o, which was the most up-to-date model at the time of data collection, and it showed the best performance in metaphor detection and cross-linguistic generalization. As an initial evaluation, we tested the model on Latin, which is a kind of low-resource language, and we achieved an accuracy of both 0.7. Then going to our pipeline, so it worked as follows. First of all, we prompted GPT-4o from the API, obviously, to perform metaphor detection and identify source and target domains for each sentence. This yielded more than 800,000 metaphorical sentences from our dataset, but then we wanted to filter only sentences with emotion targets, and we used sentence embeddings. And we retained about 30,000 sentences, metaphorical sentences with emotion target. Since we still had around 6,000 unique source domain, we categorized them using the UCRL neural semantic classifier, and it assigned each source to one of the 185 semantic categories of the UCRL semantic ontology. So this resulted in a file and dataset of around 30,000 emotion-related metaphorical sentences across 27 languages. As you can see, there is a bit of variation both in the number of sentences per language, with Africans, for example, having more sentences than Indonesian or Japanese. Sorry, I don't know if you can see my... Okay. But also variation in the target distribution, with love being more represented than anxiety or shame, for example. Okay. Next slide. Okay. Then to perform the cross-linguistic analysis, we operationalize the analysis through 3 indices, and I will go through them one by one. The first index is the target source stability index, which measures how stable each target source mapping is across languages. For example, if you see this toy example, love is a plant occurs mainly in English, so it would show low stability. Instead, love is light is shared across languages, so it would show really high stability. So we computed this index by combining target source frequency with cross-linguistic entropy. Higher values indicate frequent and widely shared metaphors, while lower values show rare and language-specific target source mapping. So you can see that from the results that some target source mapping display really high cross-linguistic patterns. If you see anger, it is mainly mapped across languages onto temperature, anxiety onto anatomy and physiology, desire onto food, hope onto light. While in contrast, love draws on many sources, but with limited cross-linguistic stability. So in other words, people tend to conceptualize anger similarly. So we get angry similarly across languages, but we describe love with much more differently across languages, cross-linguistically. So here you can see the most stable sources across languages. So anatomy and physiology, temperature, movement, liquid, distraction. While regarding targets, you can see that surprise and anger are the most stable mappings, while love shows the least cross-linguistic consistency. Going to the next index, we wanted to measure how many sources each target draws on and how they're distributed. So whether a target draws on multiple sources evenly or whether it relies always on the same source or a narrow set of sources. Okay. To capture this, we calculated the target entropy, but across sources. So higher values indicate that a target relies on a wide and relatively balanced range of sources, while lower values indicate reliance on one dominant source, sorry. So in the results, you see that love shows the highest entropy as its most frequent sources are relatively evenly distributed. So you can see from the slices in this chart, in the case of for love, that they more or less have the same width. In case of anger or surprise, which have low entropy, anger tend to rely always on the same source. So there is temperature accounts for a large proportion of target source mapping. So really quickly, a few examples. You can see that in Kazaki, sorrow is an healing wound. Rage still burns in English. We have the light of hope in Japanese. The way to happiness in Basque. Love overflows in Tagalog, and fear pulses in the back of the head in Finnish. Finally, going to our third index, it concerns language similarity. So it captures how languages converge or differ in their metaphorical patterns and whether geographic or linguistic distance help explaining this difference. So following Jeannette, we first calculated the similarity between each language-specific distribution and the overall global pattern using Spearman correlation. So all languages show positive and significant correlation, suggesting a shared cross-linguistic core structure, although with moderate correlation. You can see that Afrikaans is the language that show the most similar metaphorical distribution compared to the overall pattern, while Indonesian the lowest. Secondly, we calculated pairwise similarities between languages, again using Spearman correlation, to assess how similar their metaphorical distribution are across emotions, obviously. And all correlation, again, were positive and significant, and weak to moderate correlation. And finally, we tested whether geographic and linguistic distance, considering lexicophonological distance, can explain this variation. So geographic distance negatively correlates with metaphorical similarity, so closer languages tend to be more similar, and linguistic distance also shows a similar but kind of weaker effect, with typologically more distant languages exhibiting also more divergent patterns. So to go to the conclusion, from the target source similarity, we see that some target source mapping display really high cross-linguistic stability, while others can vary across languages. And overall, the stability differ across target, when the most stable sources are those kind of grounded in bodily experience or sensory motor experience. Concerning target entropy, they vary in source distribution. As I showed you, for example, anger tend to rely always on the same source, while others like love draw on multiple sources. considering language similarity, individual languages moderately correlate with the overall pattern, and variation among languages is partially explained by geographic proximity and typological relatedness, although with limited effect. So to conclude, as with word meaning association, emotion metaphors seem to show both a shared cross-linguistic core and language-specific variation that shapes this metaphorical distribution. So next step include seeing whether languages cluster by the metaphorical distribution, which target and source drive these clusters, and to build an actual comprehensive metaphor map. So thank you. And yes, a preprint is coming soon. So
thank you, Ginevra. We have time for some questions. There's a question from Matteo.
Sorry.
Questions from both, I think. That was a
Matteo and
fantastic.
Jeannette.
Yeah. That was a fantastic study. Thank you, Ginevra. I was just interested in maybe I missed it, but what was the accuracy? Like, did you even maybe accuracy in this case doesn't matter as much because you're using the LLMs more as an extraction kind of right to get examples and but did you have a chance to look at how accurate? Well, I was also impressed by the fact that you consider so many languages and so did you use the same LLMs like across all these languages and was the performance consistent?
Yes, so it's obviously a really good point. We use always the same LLM, which is GPT-4o, and we consider only languages for which there was at least one study demonstrating GPT-4o performance on that language. So it was kind of baseline. And we started performing also manual annotation on different languages using obviously machine translation system, so not native speaker, but different machine translation system, not only GPT-4o obviously. And the performance was quite stable across languages, I would say, so more or less across among 0.7, yes.
But how did you measure performance against like human coded data, or did you just look at the examples
yes. In this case, actually, it was not accuracy but precision. So we, for these annotation, we consider sentences that were already annotated by GPT-4o, and we checked whether they were actually metaphorical.
Perfect. Thank you. And Jeannette.
Yeah, thanks. That was absolutely brilliant. I love that. I was just wondering, some of the emotions tend to be that the words for those emotions in some languages are not always semantically equivalent, and they cover off quite different semantic space. I'm thinking particularly things like pride and shame that have quite sort of different meanings in some languages. And I was wondering whether you see that as a kind of like an issue in your study, or maybe actually as a big advantage of your study, that you're actually highlighting the way these things are conceptualized across languages. I was wondering whether that's something that you've considered.
Yes, that's really interesting. We could actually consider combining our results with other type of results, like those by Jackson and colleagues, which I showed, where they consider emotion network to see how shame, for example, is conceptualized within each language, and to see whether their networks change across the language we consider. So yes, thank you. That's really interesting.
Thank you. That's a brilliant study. Thank you.
There's a question from Tatiana.
Yes, thank you. Thank you for the study. Really interesting. I had a thought about the last index about the language, how much the language behaves similarly to the overall data, and it seemed to reflect very strongly the size of the data for that language, right? Or the number of metaphorical expressions found. So Afrikaans had this huge bar, right? It's the biggest share, and then Japanese and Indonesian are the smallest. So do you think that has an effect, and can you somehow account for or discount for it?
Yes, so we excluded the language under comparison for each correlation. So when comparing, obviously, African with the overall global pattern, in the overall global pattern, African was excluded.
Okay.
But it plays a role, yes, and it might also be related to the data set we're using. So they might change. One might be more, I don't know, the type of news that are included within the data set might play a role. So yes.
Yeah, or the lexicalization of the emotion words, like what Jeannette said, right? Maybe it's different in these languages. Yeah. Okay. Thank you.
Thank you.
There are a number of questions in the chat. I will take one, which is again going on the role of different emotions by Cristina Soriano. Any hypothesis as to why the metaphorical representation of anger is stable across languages and that of love is not?
Yes, that's a really great question. And I think this kind of works might help us understand, like, the reason for this is that I think it might be connected also to the physiological nature of anger. Like, we tend to conceptualize that also our emotional experience in the same way. So that's why temperature is so important. While love can include many more aspects of this emotional experience. So both the physiological reaction, but also, I don't know, the relationship kind of conceptualization. So not just the emotional response, but also how we think about love.
And cultural aspects.
Yes, in their culture, in its cultural aspects.
Yeah. And Francesco Mambrini is asking if we let them know when the preprint is out, and we will. We will. Okay. For the other question, we will follow up at a later stage. They are all saved. I think it's time to move to the final remarks. Thanks to the NEPLab team, we prepare a couple of slides on 2 points that might be the basis of discussion today. And I invite all of you speakers and the participants to write comments on them. Okay. While I have your attention, I would like to make some advertising for a couple of events that we will organize in the near future. And the first one is the seminar, the biannual seminar of the Researching and Applying Metaphor Association, RAM, dedicated to the topic of metaphor. It will be hosted by us in Pavia next June, and we have the president of the association here with us, Jeannette Littlemore. The call for paper is closed. The notifications of acceptance will be sent in the next few days, and the registration will open soon. So also those who did not submit are welcome to join. And I can anticipate that there will be a brilliant program. We got very nice submissions, and some have a computational flavor and are on the computational side. And the second event I would like to mention is the ExPragIT conference, the Experimental Pragmatics conference that we organize every 2 years. I'm part of the network. I chair the network. I'm not technically organizing the conference. It will be in Genova on the harbor. And the call for paper in that case is still open. It expires on April 10. And there's, in that case, too, an interest and an opening towards computational approaches. One of the invited speakers, Michael Frank, is working in computational approaches to pragmatic abilities. And of course, metaphor is a topic that is of great interest for the whole experimental pragmatics community. So please consider joining and submitting to these 2 events. So now going back to the workshop that we just had, I think that we could discuss many things, but 2 important things that I would like to launch as relevant for discussion are the following: the definition and the methods. I think that the definition of metaphor is, again, a very important, critical, complex topic. There is great variation across the talks that we heard. Fuoli et al. Use a phraseological approach. And if we check the paper, we find that it's described as a combination of MIP and Cameron's vehicle identification procedure. So basically, there's an attention to sentence level metaphors. Mazzoli and colleague used MIP approach. Reimann and Scheffler, a new version, refined version of MIP. Pedersen et al., more sentence-based perspective, also based on dictionary definition. And then we had Lieto et al., who used a more conceptual combination perspective, tracing back to Fodor and then joining the conceptual metaphor theory. Then in Tong et al., we saw again conceptual metaphor theory, but in a multimodal perspective. And our group, well, we follow the approach that Matteo and Jeannette proposed, the more sentence level phraseological perspective. Although in the second study, the MetaMap, then we eventually group the metaphors based on a sort of conceptual metaphor theory schema. So I think that there should be some, not necessarily some agreement, because metaphor can show up in many ways, but it's important to acknowledge the different definitions of metaphor that are taken in each approach. I cannot say at the moment if an approach like the MIP leads to a better accuracy, a better performance of LLM compared to conceptual metaphor or phraseological. Maybe it's in the talk, but I should go through them more carefully to say this. But I think this is definitely one topic of discussion. So I invite the other speakers to comment on it and to share considerations if they have. Please. Yeah, Matteo and Jeannette.
Yeah, I think this is really interesting, and it's also the bugbear in metaphor research that has been. And I'm just thinking, given the fact that the LLMs are drawing a lot on kind of a folk knowledge or a folk idea of what metaphor means, even though we prompt them with instructions, I wonder if they might sort of move more towards a like identification of the phraseological metaphors overall, because that's kind of what like the lay person might think of as metaphor, as opposed to things like kind of like you know, things like for our example, like
to say, like in the example they give, to say instead of physically saying.
Exactly. Yeah, that's a good one. That one we were discussing just as we were listening. Yeah, exactly. It's kind of, it is metaphor, and the reasons for it being metaphor are very solid and very replicable. But to the layperson, it may feel a little bit counterintuitive, and that layperson view may be embedded in the LLM's database. It's likely to be, possibly.
It's a very testable question, by the way. Like we as long as we can have the same data set annotated according to the two protocols and just like run the same script, and that this is partly what we're doing on the new project. Like we're testing the two different coding schemes and how the performance compares. It's very early stages. I can only say we have just some initial results that look considerably weaker than the results that we presented today based on the MIP procedure, but we haven't tried the other procedure yet. So I don't know if that's an artifact of the data, which is spoken data and it's more difficult to code, or not. So
on which data set? On which data set are you doing this comparison?
It's a data set that we're working on with a project led by Alice Dignan up in Leeds and Eleanor Semino. We have interviewed school children about kind of everyday topics, and we've identified the metaphors, both using the phraseological level, but within each phrase we've identified a kind of MIP core lexical unit that has a clear basis of comparison. So we've got the MIP and we've got the more phraseological approach on the same data set. But like Matteo was saying, it's messier data than the film reviews. It's less crafted. It's children just talking and they're cutting each other off and, you know, in conversations. So we'll see. But
we'll see.
Yeah,
we'll see. I think it's interesting also like to test it on different registers, different genres, and I expect there to be quite a lot of variation but there's always scope to rethink the prompts, rethink the instructions, and
Happy to share the effort if we want to work on multiple languages.
Oh yeah, that'd be great. That would be great.
Really good.
Yeah, maybe we can do it. We can think of something along those lines together. Sebastian.
Yeah, I wanted basically to share the same intuition that I have, that that will also explain why we were struggling to get the LLMs to run with satisfactory performance on our data that was annotated by some modifications of MIP. Yeah, compared to, for example, the relatively impressive results of Matteo, his colleagues. And yeah, I'm also wondering if this is somewhat of an artifact. It is reliance on MIP and modifications of MIP in computational approaches to metaphor is somewhat of an artifact, so to say, of how token classification in NLP was approached in the pre-LLM age, so to say.
Yeah. Tatiana?
Yeah, I would still like to add that it's a bit. I mean, I see, especially with evaluating the performance of LLMs, I think it's very important to have really clear definitions of what the actual categories are that we're looking for, and to be really specific. Because so I'm kind of hesitant to go towards a more folksy definition of metaphor, just because that might be what these models would give us, right? Because when we tried, for example, LLMs with students, with some text that the students brought into a class last year, at first the students were very impressed and they're like, oh yeah, that looks about right? But then when you look into it and you really try to give a clear linguistic definition, no matter whether it's MIP exactly or whether it's just, but you have to have some transfer of, some similarity-based transfer of meaning from one source to one target, right? That is like the minimum of what a metaphor should be in a linguistic definition. Then actually it turns out it often wasn't correct, right? And any kind of flowery language, if you throw in a poem, right? Any flowery language that's not really fitting in the context will immediately be called a metaphor, even if there's not, there's not a metaphor, you cannot define it that way. And so that's why I'm very hesitant to kind of give some leeway there to these type of models. And I would really prefer a definition that is somehow clearly delineable, right? Like that we can clearly say what's in and out. And it draws me a little bit also to the multimodal case, where I find it's much more difficult to make a clear definition of what is a metaphor or not when you talk about pictures, because there's a lot of kind of representation and projection going on anyway. I say this as a semanticist, sorry, and I will stop here. Thank you.
No, but Tatiana, I think that also in the MIP there are many cases that are not metaphor according to this transfer idea directly. Like to say could be metonymic, because it's a shift that is limited within one domain if we want to stick to the definition of it. So even the MIP runs the risk of including things that are not proper metaphor according to our intuition of it. I see Jeannette and Matteo probably have a similar comment.
Yeah, very much along the same lines. I think I want to emphasize that in our own definition, we were as strict as we could possibly. We tried to be as strict as possible. And there is definitely at the core of the definition is that transfer from one domain to the next conceptually. The only thing that we relaxed is the criterion around the units. And then we made, well, actually it's not the only thing. And then we made specific provisions for cases say that we wouldn't consider metaphorical, but based on solid theoretical grounds. So the comment about folksy understanding is more about the way the LLMs
Yeah.
gonna tend to behave in their identification of metaphorical expressions, which might be informed by this more intuitive, if you like. I think a phraseological approach seems more intuitive because you're not going word by word and checking a dictionary. That's not how we tend to interpret metaphor in naturalistic discourse in naturalistic situations. That's why we mean. And so,
Yeah.
but we totally agree with your point that definitions need to be rigorous and applied consistently.
Yeah. And I think it's important to consider that there is also the pragmatic view of metaphor that matches a bit better with this phraseological definition. Although in pragmatics, metaphor is not a natural kind, so it's not an autonomous type. It's just along a continuum of loose uses of languages, and so it's a matter of degree and how extreme these loose uses. But anyway, I mean, we could continue this discussion, but we will not. But we identify one important topic that needs to be considered when approaching metaphor and LLM. And the second one, I think, it's the variability of models: small, bigger, proprietary, non-proprietary. And here as well, there has been a great variation. And Chiara Barattieri di San Pietro, among the organizers in the workshop, put together this slide while the workshop was going on. And perhaps, Chiara, you can share some considerations.
Yes, sure. Thanks, Valentina. So this is a very preliminary summarization of the methods that we've heard of today. So sorry if there are some inconsistencies or inaccuracies. It might be possible. My consideration is that when the authors compare the older and newer version of LLMs, so resources based, for example, on BERT models and GPT models, well, the results seem to be very clear. So we are actually moving to LLMs, big models, because they're working better. And the caveat that I would like to share is that as far as I've heard today, closed models seems to work better, which is a little bit annoying, if I might say. I would like to see open model to perform better. So maybe something we can work together as a community is to try and understand why there are these discrepancies, and probably we should collaborate with developers to try and make open resources more performant in this kind of in this sense. So this is my at least my wish. And another consideration is that prompting seems to be methods that works quite well. And for these reasons, I would like to see and to reason about the structures of prompting that we are using as a community, because at one point I think we may want to compare our results. I'm not thinking about a real meta-analysis, but maybe. But in this case, we should make our methods really comparable. So I think there's a lot of variations in terms of prompting. For example, I'm thinking about the question that Matteo asked before, because it was right. It was a nice question. It was not clear how we prompt the model. And yes, again, as a community, I think we should reason about this. If it is the case, to make our methods more comparable in this sense. Yes, I would like to know what the other people think about this.
Yeah, Sebastian.
Yeah, I mean, I totally share the worries that you mentioned a bit with respect to the closed source models. Because yeah, I mean, if you look at the performance of the more open source and the models that can be run locally, I mean, if you compare them to like encoder only model, they fall a bit behind, and even like the smaller encoder only models are better, and maybe it should not be completely abandoned because like they have achieved like in previous research like F1 scores of like 70s 75%. I mean, they have their caveats that I very kind of detailed in a very detailed manner analyzed in several publications and in my PhD thesis. But I think we should not completely abandon them, so to say, because I mean, yeah, like the flagship closed source models outperform even them, and they outperform well, but still, yeah, there is some trade-off like that needs to be done because it's expensive. I mean, we haven't really done any prompting experiments on our data with like the very large GPT models, but already like calculating through it seems like a high amount of cost. And yeah, besides all the other negative aspects of like closed source LLMs.
Yeah. There's a trade-off in the resources that we have access to and the best resources that we should use. So you're right. It's not an easy task. I agree.
Xiao, you?
Right. As for prompting, I'm not sure if it really can be comparable across studies because but within each study, I think the norm is always to do some prompt engineering to optimize the results. Yeah. And also for this reason, because to reach a higher performance for this specific study, then of course maybe the prompt technique cannot be exactly replicated by another study that has a different purpose.
Yes, I agree that prompting it's called prompting engineering at this point, but I think it's more like a prompting art because we tend on fine tune our prompt on an incremental basis, like trying several times to see what's is giving us the best results. But I share the point that this makes our methods a little bit not so much comparable, and I think this is this is an issue. This is a problem.
Maybe, but at least I think it's comparable. Like for if both studies use zero shot, then zero shot prompting can be compared to zero shot, and few shot can be compared to few shot. So yeah.
Yes, you're right. Yes, at the macro level, yeah, you're right.
And also just a little bit correction. For my study, the task is well much more than meant for identification.
Of course. Again, sorry, that was just sketching it down while hearing presentations.
Done on the spot just to favor the discussion, so it's not accurate. It's not a meta-analysis yet. Matteo and Jeannette, perhaps for the last comment of the day.
Thank you very much for this overview. It's brilliant, and I agree. We need this kind of bird's eye view and kind of take stock of what everybody is doing to learn from each other. And so something along the lines of this is super helpful. On the prompting, there are templates that I think might be shareable across different studies. And then, of course, the specific implementation of those templates or those schemes might differ because it has to differ. But that's also the nice thing about LLMs and how flexible they are. I would like to highlight Weihang's comment in the chat. Huang is one of our co-authors, and he has a very deep knowledge of LLMs and has used small LLMs in very clever ways. So I think what his research shows, what a lot of the research here shows, is that different models of different sizes can and should be used for different purposes. Like things like the negative log likelihood, surpriso, the more the less prompt-based kind of methods, it seems to me that small models are just as good as large ones, if not better. And so whenever we can use a small model, I think we should use a small model. And large proprietary models should be avoided as much as possible for a whole host of reasons. But for complex tasks, it seems like that is they are just better for whatever, they're more data, more complex kind of algorithms running in the background in addition to just the next token prediction. So yeah, maybe like have a menu of models and try to test them out and have like potentially a bit of a set of guidelines for when to use which model.
You're right, and I totally agree that we should not abandon smaller models, which are in fact more explainable than larger models, and continuing working on them might in fact help us go through those details of the theory that we cannot address with larger models. So it could really inform the further steps. So totally agree that we should not abandon them and continue comparing them with larger models. Thanks.
I think that it's time to conclude, but definitely I will follow up with the participants and possibly others to produce out of these events either a special issue or perhaps some guidelines. We should discuss what is most fruitful at this stage. But for all, I just wanted to remind to follow the YouTube channel and Instagram page where we will post about the recordings and next event about this large language metaphors initiative. Okay, so a big thanks to all, and it's time to conclude. Thank you.
Thank you all. This was a great.
Thank you.
Bye.
Thank you. Thank you.
Bye.
Thank you very much.
Bye bye.
Thank you. Bye.